as you can see, we're going to go with the good old Sharpie and paper. Let's see how this goes. So let's get right into function notation. So today's video we're going to be looking at something like this. When we have something like this, we can look at it and say, or we can represent a function in terms of f of x, where f of x is going to be used to represent the value of the dependent variable, which is f, for any given independent variable, which is x. So it might look something like f of x equals x squared. Usually we're used to seeing something like y equals x squared, but now we're going to represent the function f of x. So whatever x is, we can plug into here and represent it like that. So it might make more sense if I just get into an example. So let's say we want to write a function for temperature, and let's say we have a problem where we have a temperature that is for some, say, system or some component or whatever, like we were talking about. Say it's at 11 degrees Celsius, and every day that passes by, we add 0.015 degrees Celsius. So let's say we want to represent this in a function t. So let's write that out. Let's write t of, and let's pretend like day is a letter D. So t is our independent variable that can change. It doesn't depend on anything. But t, the value of t does depend on d. That's why this is the dependent variable and that's the independent variable. So we're going to write t of d is equal to 11 plus 0.015 d. And now we say, like, where t represents the temperature in degrees Celsius and d represents the number of days that has passed by. So, and in this, or let's try something, or let's just change this slightly. Instead of saying, let's make it easier, 5d. That way we can easily map this out, or like write it out. We can say that, okay, if this is the function for temperature, let's say temperature T, and let's say on day 0, let's put that in. T of 0 is equal to 10 plus 5 times 0. 5 times 0 is 0, so it's just 10. So now let's do 1. Let's do, and now we have 10 plus 1 times 5 is 5 plus 10 is 15. And we can keep doing this. We can put a 5 here. T of 5 is equal to 10 plus 5 times 5 is 25 plus 10 is, and we can even map that out where D is here. We is our line. So function notation is just a different way to represent the function. And that's what we see here. So let's try one more example. I'm just going to put this here, and here I'm going to basically just write two functions. F of x is equal to x squared minus 3x. And I want to write g of x is equal to 1 minus, I don't need this, sorry. So now let's push into a problem. Let's do this. Show f of 2 is greater than g of 2. Let's prove this. And that is as simple as saying, okay, f of 2 is basically 2 squared minus 3 times 2. That's all it is. I put in the 2 where the x is, and now I can solve this. Negative 2. Now we can do g of 2, which is 1 minus, well, yeah, 2 times 2 equals 2 times 2 is 4. So now we know that f of 2 is negative 2 and g of 2 is negative 3, and negative 2 is greater than that. So that's how we show that g of 2. These 3 dots is my way of saying therefore. That's how I got into the habit. Let's say we want to do something even more weird. Say we have something that says, show me what this would look like. G of 3b. B is now a new variable that I want to sub into x into this formula. That's very simple now. I just do 1 minus 2 times 3b, which is equal to 1 minus, and if I expand that, negative 2 times 3 is negative 6, and negative 6b. That is g of 3b. I can also do something a little more complex, which is let's see, something a little more complicated. Now, let's say I want to find out this. This is very, don't let it confuse you. Let's do this one at a time. Let's do for f of x first. Let's do x squared minus 3x. And let's plug in c plus 2 squared minus 3 times c plus 2. Right? And then on this side we have 1 minus 2x, which becomes 1 minus 2 times c plus 2, which becomes 1 minus 2 plus 2 squared. So then we have this negative 3 times c, which is negative 3c minus 6. So if we're looking for this, we have f of c plus 2, which is this entire thing. Well, wait, let's simplify this. Let's c squared. We have 2c's, so 4c minus 3c is plus c plus 4 minus 6. That should give me negative 2. So that's what we have. And that one too, 1 minus 4, I can do negative 3 minus 2c. So now I have this is that and that is this, but to find this entire expression I need to subtract this from this. So let's write that out. C squared plus c minus 2 minus, and because I'm subtracting these terms here, if I was to open this bracket, it's kind of like I have a negative 1 in front of it, so I'm going to multiply that negative 1 into each of them, and that'll give me negative, negative, positive, negative, negative, positive. So that'll give me plus 3 plus 2c, and I have c squared plus c minus 2. Now I just need to add, collect the like terms, so I only have 1c squared, and then I have a plus c and another positive 2c, which will give me 3c plus 1. So this entire expression is equal to these functions are defined here, and that is how we solve using this function notation. So yeah, I hope this was a good intro to our grade 11 math series. Hopefully this made some sense, and yeah, that's it for this video, and I'll see you in the next one. Okay, welcome to another video on math. Today we're going to be looking at parent functions. So parent functions are basically, let's just write out a few. That would be considered a parent function because from this we can make a whole bunch of functions. We can do mx plus b, like any kind of format with a slope and a y-intercept. We can do 10x plus 1. We can do 1. We can do x plus 3 or 2. This is what's considered a parent function, and from that we can create all kinds of child functions. Another one we can do is like our quadratic one. So we can have f of x equals x squared, or we can do 2x squared or x squared plus 5, or x minus 5 squared, or all of them 2x squared, 2x minus 5 squared plus 5. And so yeah, all these functions are children of this parent function. So today we're going to look at the main parent functions that you're going to see quite often in the upcoming many videos. There's also, this is called the square root function. Well, let's just write the linear. Let's write this one. The square root function. And then we have, let's do the reciprocal function. And then we also have this is the absolute function. Well, this is the absolute function. So let's look at these functions one at a time. So basically, let's do the linear one first. And this is very easy to understand once we map it out. Like, say we put in 0 for x, this is 0. We put in 1, that's 1, 2, 2, dot, 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 100, 100, right? So, this graph, that's not straight at all, will basically be this. And obviously, well, this is the parent function. If you were to modify it like x plus 1, it would be here. And we know that from our previous year's lessons. That is our linear. And let's do the quadratic one. F of x equals x squared. So at 0, we have 0. 0 squared is 0. 1 is 1. 2 is 4. And remember, this is x. This is f of x. 3, 9, 4, 16. So we know that this is going to go like this. 0, 0, 1, 1, 2, 4. But also, if you were to plug in -1, you still get 1, because -1 squared is also 1. Same with -2, -3, -4. You also get the same values. So at x, at these negative values, you also get the same. I'm trying to be creative, artistic here, or not so creative. So yeah, and this is my quadratic. Let's do the next one. F of x is equal to root x. And when we do this, we will get, let's just start plugging some numbers. Square root of 0 is 0, square root of 1 is 1. I can do 2 as well, but it's going to be a very weird decimal number, so I'll just skip to 4. 4 square root is 2. Let's do 9. Square root is 3. So if you were to graph this out, 0, 0, 1, 1, at 2, 3, 4, you'd get 2. this, as it curves up a bit and goes to the right, that is our square root function. Pretty straightforward. Next we're going to do the reciprocal function, which is so here, if you put say, I'm trying to explain this in the best way I can. Say if you put 0, actually you can never put 0 here, sorry. You can't have 0 as a denominator, so this function will never touch 0. It'll get close to it, but it'll never touch it. So let's do 1. 1 over 1 is 1. And as this number gets bigger, let's say at 2, this is going to become 1 over 2, so 0.5. If it becomes 4, it becomes 0.25. Right? So it'll keep getting smaller. So that's going to go like this and get very close to the x-axis but never touch it. And actually, if this gets smaller, if x gets smaller, instead of saying 1, 2, 4, if I put 0.5, 1 over 0.5 is 2. So that'll be 2. This is 0.5 here, and that's 2. And the smaller this number gets, the bigger this number gets, so that's going to go up that way. And that is a reciprocal function in the positive side. However, if I was to plug in negative numbers here instead, say I put this negative number here, I'd get a negative. That'd be here. Same with this. Negative 2 would be negative 0.5. Same with that. That should not be touching, but just pretend it doesn't. So this is what our reciprocal function looks like. It gets really close to it but never touches it. And the only one left is the, I guess the absolute one. I can draw that here. That is the same as our linear function. F of x equals x, except instead of that, the absolute value of something just means that if it is a negative number, so say negative 1, the absolute value of negative 1 is just 1, the positive version. So while in here, if you had a negative 1 input, you would have a negative 1 f of x that's here. But in this function, we don't. If we put 1, 2, 3, you get 1, 2, 3. But if you put negative 1, negative 2, negative 3, you still get 1, 2, 3. So at the negative x values, negative 1, 2, and 3, you're still getting positive y values, or sorry, f of x values. And this is our absolute function. So yeah, there you have it. Our five parent functions. Let's just recap here. This f of x is going to be a linear function. Our square root function, that's the quadratic. Our quadratic parent function. Our reciprocal function, the 1 over these are very rough sketches. Our absolute and then our square root function. And there you have it. Our 5 parent functions that we're going to be abusing in the next several chapters. So these are the basics, and then we're going to start manipulating them, and I sound like a very toxic teacher right now, but don't worry, this is all going to be very easy once we understand these functions and how they look, and then once we apply changes to them, they're going to be very simple. So that is all for this video on parent functions. And yeah, I shall see you in the next one. Okay, so today we're going to be doing domain and range. So domain basically refers to all the values in the x direction, and range is all our y values. So when asked to state the domain and range of a specific relation or function, they basically want you to define or explain or say that, listen, this is what all the x values are allowed to be, and this is what all the y values are allowed to be. So let's look into one. Let's have an example. It's not perfect. Let's do and say we have at 1 we have 2, and then at 2 we have 3, and then at 3 we have 4, and so on. So let's say we have these points, right? And these points are, if we were to map them out as x and y coordinates, at -3 we have a value of -2. At -1 we have 0. At 0 we have 1. At 1 we have 2. At 2 we have 3. And at 3 we have 4. So now we're going to basically write the rules for domain and range. Let's start with domain. The domain for this is basically what are our x values allowed to be in this particular set. This is a limited set, so we only have these 7 points. So we can write our domain is equal to literally these points. And same with our range. So we can write -2, -1, 0, 1, 2, 3, 4. Or there's another way to write this. We can write x is equal to all the integers between -3 and 3. So this then, well, this basically means this. X is all the integers in this range, domain, but like within these two numbers. We know that from -3 to 3, it's every integer. And same with the y. And I put this sign here. This means A is less or equal to B, or B is greater or equal to A. That's what this sign means right here. And the opposite is exactly what you think it is. Well, yeah. Basically whatever's on the opening side. That's what this means. So yeah, because we do have values of 3 and -3, so we do use the equal. If we were to use, instead of this, we were to use just this, it means B is strictly greater than A, and they cannot be equal. So, yeah. So in that case, you could write this as -4. So the integers greater than -4 and the integers less than +4. So yeah, that's one example. Let's do another one. Let's do one where we have, let's say we have -5 and we have a +5 and a +10. Let's say we have a line, let's say that's 5. Let's make another line here that goes from -5. I'm gonna draw an open circle and let it go till there. Oh no. Ignore that part. Oh, let me draw that again bigger. Let's draw this, and it goes to here, and that's a closed dot. And then let's do somewhere here, let's make another one, an open dot, and go till just past 10. Okay, now that we have this, let's look at the domain and range for this function. So one thing that I want to point out is that when you have an open point like this, it means this point is not included, but a closed point is let's say this line happens at 2 and this line happens at 6 on the x. So right away we know the range, Our range, our y values for this particular function can only be 2 or 6. There's nowhere else that y value is going. But for our domain, we have from -5 to 5. That's one domain, right? But remember, the open one is not included, so it's not. So from -5 to 5, this 5 is included, but this 5 is not. So if you were to write that, we could write is because you'll notice I didn't put the equal sign here because this -5 is not included. But this 5 is, even if this one is open, this one is included. But let's say this ends at 11. So actually the range will continue all the way to 11. And that is the domain and range for this particular function. Let's do one more, or even maybe two, but let's see. So let's say we have let's say at 3, 1, we have a parabola that opens up. Sorry, it is 1, 3, x and y. So now the domain and range for this. Let's look at the range first, or let's look at the domain. The domain, as we can see, as this continues, this will go on forever in that direction, and this will go on forever in that direction. So our domain is XER, and that basically means all, like any real number, x is equal to all real numbers. And then for our range, we just have to look at x is all real numbers, and the only restrictions we have, because from here and downwards we have all our y values, but from 3 and upwards we don't. So oh no, I don't know why I put x. It should be so the only condition we have here is that our y value can only be less than 3, and that is the domain and range for a parabola. And if you wanted, we could even do, let's say we had a circle with a radius of 5, and its center was at the origin 0. we know that our x and y values will go all the way from, like say, let's do our x first. Our x can be all the numbers from -5 to 5. We have a value for every x. Same with y. So for a circle, it's very easy. Our domain is XER. Let's do -5. -5 to 5, and same with our y. And that has been domain and range. For functions, you might be asked in the future to write the domain and range for a function after solving it or something. But basically just look at all the x and the y values, what they can and cannot be. One thing you'll notice is that I went from XEI to XER. When I say I, that means integer. So I use that for this one here. These are integers because I have plot points. I don't have anything in between. So I don't have a -2.5 for x or a 0.5 or 1.5. I do have integers. Integers are strictly 1, 2, 3, -1, -2 are whole numbers. But when I use XER, this is x is equal to all real numbers. So real numbers, any number. It could be to any number of decimal points. It could be here, 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 here. Like, yeah. Well, I just noticed I could write this as I. But yeah. Sorry about that one. This one. Our range. Yeah, our range is YE. That should be R. Sorry. That should be R. This could be YEI. Well, that's not necessary. We only have 2 points there. But yeah, I hope this made some sense. And I shall see you in the next one. Okay, so in this video we're going to be looking at the inverse function. So basically the inverse function, it sounds a lot more complicated than it actually is. But an inverse function actually is the reverse of a original function, which is exactly what it is supposed to be. So let's look at an example. So let's say we have a function f of x is a function of x, and the function is 2 minus 5x. This is the original function, and this is a linear function. So in order to inverse this, like what this does to x, like what this f of x value depends on is what happens to x. So x is being multiplied by 5 or -5, and then it's being added to 2. So it's actually positive 2 minus 5 times x. That gives us our f of x value. So to inverse this function, we need to do the exact opposite. And the easiest way to do this is to swap x and y values. Or, sorry, variables. So let's say we have this example. And what I'm going to do first is put a y here instead of f of x. And then I'm going to swap it. After swapping it, now I'm going to solve for y. Basically, I'm going to get y alone. This is just some simple algebra. And that will give me my inverse function. So, one of the first things I'm going to do is I'm adding 2 to this side, so I'm going to subtract 2 from both sides. And that'll give me x minus 2 equals negative 5y. So I have negative 5 being multiplied on this side, so I'll divide both sides by that. So now I'm left with y is equal to this, which if you apply the negative, it should be 2 minus x over 5. And this is your inverse function. So if f of x is equal to 2 minus 5x, our inverse, and this is how we notate inverse, is 2 minus x over 5. And yeah, the inverse is also a function. So that's how we do that. So let's look at another example. Let's look at a plot. Let's say we had one, two, three, four. That's negative 4. Let's say we had 1, 2, 3, 4. That's positive 4. Let's say we had 1, 2, 3, 4. 1, 2, 3, 4. So let's plot some points. Let's say we have a point here, here, here. Let's put a point up here. Let's put a point down here. And then let's put a point right here, negative 4 comma negative 1. So now let's say I have these points and I ask you to graph the inverse function of this. And this is actually very straightforward. It might confuse you, but what you can do is let's draw an imaginary line. Let's say it's going and this imaginary line is basically y equals x. So now that we have this imaginary line, now I'm going to plot a mirror of everything, basically. So remember when I said we're going to swap the x and y coordinates, so you'll notice that let me just put a notation that what I'm going to do in orange is our inverse. So right off the bat, if we have a, let me just use both. If we had this point, -3 comma 1, this will become -3, and same with all of them. So this will become right here, and that is basically a mirror of that. Same with this one. -2 comma 1 will become 1 comma -2. Same with this one. 1 comma -1 will become, -1 comma 1 will become 1 comma -1. You can see that it's a direct inverse. This one, we can just eyeball it and we know it goes here. And that's that. Like, let's look at this one. 4 comma -1. That becomes -1 comma 4. That's -1 comma 4. That's all the way up here. Same with, what else am I missing? Oh, this one. I have 0 comma 3. That becomes 3 comma 0. And our 1, 2, 3, 4, 5, 6 points have been plotted. 1, 2, 3, 4, 5, 6. And it's as simple as that. So let's do one more. And this one is going to actually be a function, a linear graph. Can't use that side. Let's do a proper function. Okay. Those are just intercept points. I'm gonna try to draw a line here. And this is going to be y equals g of x. So you might be wondering, maybe I could find the slope and the intercepts and create the full function, dy equals mx plus b function, swap them, and then write it out again, x minus b over m equals y. You could get the inverse function like that and then plot it out. Or, because that would, you would also have to like redo this or move this around to become into this format. But it's too much work. I know right now that we have the intercepts here. for our g of x function, we have 0, comma, let me just write it here. Our y-intercept is equal to 0, comma 4, and our x-intercept is equal to, I want to say that's, that should be 5. I'm a little bit off here, but it's okay. Let's put that as 6. Our x-intercept is 5, comma 0. So when we want to do the inverse, let's swap these around. Our y-intercept will become, we're going to swap the 2, and that'll give us that will give me, this point will be mapped to the inverse. So 0, comma, sorry, I don't know, I must be half asleep right now. I'm just confusing myself. This is a 3. So our new value will be mapped here at 3, comma 0. And that is confusing. So our y-intercept will go from, our y-intercept, which was 0, comma 3, will invert and become 3, comma 0. And that'll become our new x-intercept. And our x-intercept, which was 5, comma 0, will invert and become our y-intercept. Well, this is going to be 0, comma 5. 0, comma 5, that's up here. And that is my new line. So this is y equals g of inverted of x. Wow, I actually confused myself there. But happens to the best of us. Just gotta retrace your work backwards. And yeah, that is just taking it one step at a time, and yeah, that's all for the inverse function. I'll see you in the next video on to something maybe more confusing. Okay, so in this video we're going to be doing function transformations. So in our previous videos we learned about parent functions. So that is going to be something we're going to be looking at today. So let's jump right into 2 different functions. Let's do y equals and so we have these 2 functions, and basically we want to see how the difference in these 2 values, like both of these come from this function, are quadratic. The only difference is one has a positive 4, a positive integer in front of it, and the other one has a fraction. So let's look at how that happens. So let's do this. So let's say we have a regular quadratic. And now let's put in this one in green. So this black one is our x squared. Now our 4x squared is going to be slimmer. And that is because if you were to write out these, say, x and y values, you would have, when this is 0, this is 0, this is 1, this is 1, this is 2, this is 4, this is 3, this is 9. However, for this one, for y equals 4x squared, for the same x value at 0, it's 0, but at 1, when x is 1, we have 1 times 4, and 4 squared is 16. That's why at 1, instead of like where we may have had 1 here for the x squared, we have 16 all the way up here. That's why it becomes more narrow. And similarly, for this one, for x equals 0, we have 0. And let's do x equals 5. At 5 now, we have 5 times 1 over 5 is 1. 1 squared is 1. So now, at x equals 5, which is all the way here, we have a 1. So, by that logic, you have something like that. It's a much wider one. Is how we can see how these function transformations impact our function. And we'll do one more. Let's do our absolute graph. If you remember the absolute one. That is this is our absolute function, where, -1 is 1, -2 is 2. And now we're going to do the same thing as before, but now we're going to use these two functions. And we're going to see how this impacts our graph here. So let's do this one first, 0.25x. So if we were to write this out, x and y. Remember, x is being divided by 4. 0.25x, which is our y absolute value. So let's write -4, and that'll give me 0.25 times -4 will give me -1, but the absolute value of that will be that. And same with 0 will be 0, 4 will be 1. So before at -1, well, here we had -4 was 4, and 4 was at 4. So say these two are 4, and that's 4, -4, sorry. And now at the same x values, it's now at 1, somewhere here. So as you can see, that's a straight line. And now we see with a fraction here, or this could also be written as the absolute value of x over 4. We have a wider graph. Okay, well, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be transforming the root function, which, as we recall, is f of x equals root of x, right? So in here, the best way to go about this is to just simply try to graph something in the form of the root function. So today we're going to try to graph out this function here. So we know that this is our parent function. And we're going to do this one step at a time. So from previous videos we know that this -1 is our vertical translation. So that's and we know that we're going to have this number 2 is going to give us a horizontal compression. Or don't, let's do the other translation, the horizontal one. And this horizontal translation is going to go 4 units to the left. And then we're going to do our horizontal compression. Enough space. By a factor of you'll see why that's half in a second. And then we have a vertical stretch by a factor of 3, which is that. And then I almost missed that, it's the negative sign. So we're going to have a reflection on the x-axis. this this function, this parent function, that will get us from here to here. So let's start by writing this out, or sketching this out. So let's put this at 0, and let's do 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So we know that our original function is going to look something like this. This one right here, f of x. Our coordinates at 0. X value, we're going to have 0. At 1, we're going to have 1. When we have an x value of, say, 4, then we're going to have 2, which is here. And so 1 to 1, 4 to 4, 4, 2. And then we also have another 9, 3. So when you plug in 9 as x, the square root we get is going to be 3. That's our y value. So that is going to look something like that. And then we're going to start doing our transformations to it. So let's do this 2 first, right here. This 2 is going to be a horizontal compression. So what happens when we start writing the 2 out? F of 2 of x. At 0, we still have 0. But now, our horizontal compression, so when we have, say, a half now, to get the same output as 1, in order for this to be 1, now we have to put, because now this is 2x, so this is basically this, y equals root 2x. So in order for this to be 1, this entire side has to be 1. And that's only true when you have 1 under here. So if x half times 2, that'll give me 1 under the square root. And that will give me 1 to 1. And that same goes for here. To get the same value 2, I can't put the same x here. I have to put 2x under the bracket. So 4 over 2 is 2. And then same with 9. So instead of 9, at 3, my x value will now be 4.5. So now, if I was to write the exact same coordinates here, now at half, I have 1. So half of, so before it was 1 to 1, it was there, so now it's about here, smaller, and then 2, 2, and then I have 4.5, and that's 3, which is somewhere there. And that's how my y equals 2x. And understandably, if I was to put a smaller number there, like instead of 2x, I put 1 over 2x, these numbers would have to be bigger, so it would actually be thinner down here. because right now it's a horizontal compression. So now that we've done that, let's move on to the next transformation. Let's do our vertical factor of 3. So now we're going to have 3 times f of 2x. So now, whatever this was, now we're going to have to put in, we know 0 is going to be the same. But now we have a vertical stretch of 3, so whatever this was, we're going to multiply by 3 to obtain the values that we're looking for. So for at half now, our half was over here somewhere. Now instead of that value at 1 over 2 is going to have a vertical stretch of 3. So my y value is going to go from 1 to 3. And same for here. So 1 over 2, and now it's going to be at 3. And for my value at 2, what I had before was 2. Now it's going to be 6. And what I had before for 4.5, now it's going to be 9. That's about here. And that's y equals 3 root 2x. So now let's do another transformation. So far it's pretty straightforward. Let's do our reflection now. Let's do the reflection. So now our reflection is going to be on the x-axis. So now instead of 3f of 2x, we're going to do negative 3f of 2x. So now, whatever we had before for our x as the, now our output, basically, so let me write that one out too. So this one here is y equals 3 times 2x. So whatever the last one was is multiplied by 3. And now the output, our y value, is going to be the negative of that. So our y values here will become negative, except our origin. So same with our 1 over 2. That's going to be negative 3. Our 2 will become negative 6. Our 4.5 will become negative 9. So let me So now let's draw this one. So we're going to have this value flipped. So that will become from 3 to negative 3, and at 2 we're going to have, instead of 6, we're going to have negative 6. And then at 4.5 we're going to have negative 9, which is somewhere here. So now you can see So here, these two. So we're gonna go down 1 and left 4. So each one of these points will go down 1 and left 4. So we can actually write that out here. So this will now be -3. So we're going to have something like this. So our origin is now going down 1. So our y value is being decremented by 1. And then our x value is being shifted over left. So -4. And now I can just do that with all of these. So 0.5 minus 4 is -3.5. 2 minus 4 is -2. 4.5 minus 4 is 0.5. And same with these. I just subtract 1 more because I'm going down. So now I'm -4, -7, -10. Now these are now my new points. So -4, comma, -1. Now I have that point. That's my origin. So this one went -4 and down 1. My next point is -3.5 and -4, which is somewhere here, which is that point. And then same with what do I have here? I have -2, comma, -7. And then I have 0.5 at -10. And that is my f of x, the original one. So yeah, now we see how step by step we can move the graph. And one more thing we can do is just quickly state the domain and range. So our domain is how many x values we have. So x we know starts from -4 and we'll go that way. So x will be greater or equal to -4. Why not exceed r? And our range is going to be, I think the highest y value we have is -1, and then it only goes down. So our y is going to be all real numbers, but limited to y is greater or equal. Sorry. Y is less. No, I had it right the first time. Y is less or equal to -1. But yeah, x is going to continue in the positive. Y will only go down. Okay. So that's what I have, and I'm going to give myself full marks. So yeah, that's all for this video on transforming the root function. I hope I didn't confuse anybody, and I hope the colors helped. But yeah, I shall see you in the next one. Okay, so in this video we're going to be adding and subtracting polynomials. So basically we're going to be looking at polynomial expressions and trying to figure out how they work and if they're equivalent to each other. And we'll just start with an example. Say we have two functions. Function 1, and that is -5 t squared plus 100t plus 1000. Let's say I have another one. Another function, this one is negative 5t squared plus 75t plus 1200. And say we find the difference between these two. Say we want to do this. F of x is equal to f1 of x minus f2 of x. So that minus that. Now if we were to write that out, that would be negative 5t squared plus 100t plus 1000 minus the polynomial of negative 5t squared plus 75t plus 1200. And this could easily be simplified down to, if you were to open the brackets, you'd be adding these three. Or you can even just look at this here and just work downwards. Like, you know how we used to do substitution or elimination. So these will cancel out. And you're left with adding these two. 175. No, hold on. Yeah, 175t. Because I'm subtracting. Let's open the brackets and do this one step at a time. So we have a subtraction here. So we're going to do plus 5t squared minus 75t minus 1200. So let's simplify that. These two get cancelled. 100 minus 75 is 25t. 1000 minus 1200 is 200. So now I have this function. I'm going to call this g of t. G is a function of t. And now I also have this ginormous function here. So I have f of t and t, f of t and g of t. So that is our function simplified when I open the brackets here. But we can also say that this function here on a completely different problem is also equal to now can this function here be equal to this function here? And the answer is that these two functions are not equivalent. What you need to understand about the two functions, one being simplified step by step and the other one being simplified by skipping many steps, you need to understand that polynomials behave like numbers. For any value of the variable, the result is a number. So whatever this is, it's going to be a number here. So if you were to do subtraction or even like elimination, then you can see that adding the opposite of the second expression, you can collect like terms and end up with this. that this secondary function here is not equivalent to our initial function. So let's try another example of like when we look at equivalence between expressions. So let's do something like this. So this is our first function. And now let's do this is our second function. Now I want to see if this is these two functions are equivalent or not. And the way you do that is simply by plugging in some numbers. So let's just put in x equals 0, y equals 0, z equals 1. And when you put these numbers into here, well, yeah, that's a very easy way to check. We can do 0 times 0, 0, which is 0. 0 times 1 plus 0 times 1. This will be 0, this will be 0, this will be 0. That is a big fat 0. But here, if you do 0 squared plus 0 squared plus 1 squared, you actually end up with 1. So you can say, therefore, these expressions are not equivalent. So, one thing you can always check if you have two different functions, say their lines y equals mx plus b, in two different forms. You have one here and two here. For these two, let's say that line is like that. For this expression, it could be like, say, y equals 10x plus 10, right? This could be y equals 10x plus 1. These two are in fact the same, but these two functions have to have the same graph, and that's how we can tell. And also, if I was to plug in like 1 into this, I get 1 plus 1 is 2, this is 20. If I put in 1 here, I get 1 times 10 plus 10, which is 20. But if I was to plug in like 10 times 10 is 100, plus 10 is 110. Let's do 10 here. 10 plus 1 is 11, times 10 is 111. And that is how we check for equivalency. That's probably wrong. But yeah, that is all for this video. shall see you in the next one. Okay, so in this video, we're going to be learning we're going to be multiplying polynomials. So let's start with two functions. So now that I have these two functions, I want to multiply them. I want to find and that is exactly what it looks like when you imagine it in your sleep. And that's how we're going to go about doing this. So we can do this like in our previous videos we've actually done this, but here we're going to open this up using the distributive property. So we're going to do the negative 10 first into these three. So it's going to go in like and then it's going to go in like this, the 5. So let's write that out. So let's do these ones here. Negative 10 into negative 5t squared, negative 10t into negative 5t squared. That's going to give me a positive number. T times t squared gives me t cubed. And then if I do that with that one, I should get negative 50 t squared. And then I should get 2.5 times 10 negative 25, I believe. Yeah, so the decimal will go over. And then here I have, well, this is going to change its sign. Negative 25t squared plus 25t plus 12.5. And now, if I collect the like terms, I can do minus 25t plus 25t plus 12.5, so these will cancel. And I'm left with these two adding to negative 75. And here we have it. That long number, or that long expression, has been simplified to this. Let's do another one. yeah, let's take it from here. First, let's multiply these two. X squared plus 2x plus x, so plus 3x. So if you are confused, I multiplied that to that 2 and that to that 1. So I get 2x plus 1x is 3x plus 2. Now, let's multiply this binomial into this trinomial. So now I have this 3 is going to multiply to this trinomial, this x is going to multiply into that trinomial, so I have x cubed plus 3x squared plus 2x plus 3x squared plus 9x plus 6. If I group the like terms, x cubed, I have 3x squared and 3x squared, that's going to give me 6x squared. And then I have 2x plus 9x, that's 11x. Then I have 6. And here is my formula for this rectangular prism, for its volume. And that's a way we can use math to figure out or make expressions for things. Let's look at one more. Like if we wanted to do this the other way, let's say I wanted to multiply those two instead from the start, right? I could do v equals x plus 1 times, let's multiply those two, x squared plus 2x plus 3x, that would be 5x plus 2 times 3 is 6. If I was to multiply that, I can do, let's multiply the x inverse, x squared plus 5x squared plus 6x, and now let's multiply the 1 plus x squared plus 5x plus 6. This should be cubed, sorry. Again, let's do this. 5x squared plus this cube, the only one. 5x squared plus x squared is 6x squared. I have 6x plus 5x, that's 11x, and I have 6. Same. And yeah, let's do some more. Let's look at this. I have I have these two functions, and I want to know, are they equal to each other? And from our last video, we saw that we could do this by simply subbing in a number. Let's do x equals y equals z, and they're all equal to 1. If I plug into 1 into all these, it's 2 times 1 plus 3 times 1 plus 4 times 1 squared, and that'll give me 2 plus 3, which is 5, plus 4, it's 9. 9 squared is 81. But here, if I plug in 1 into here, 4 times 1 squared plus 9 times 1 squared plus 16 times 1 squared And since this is not equal to that, we say that they're not equivalent. Another thing we could do is this side here is expanded, whereas this side is factored. What we can do is expand this and see if it actually equals this in the expanded form. So that trinomial being multiplied by itself is the equivalent of saying and now we're going to do this one step at a time. Let's do the 2x first. I'm going to multiply this guy by those three. So 2x times 2x, that's I already messed up. Starting on 4x squared plus 2x times 3y is equal to 6xy. 2 times 2x times 4z is equal to, that's that one. Now let's move on to this one. 3y times 2x, it's going to be 3y times 3y is going to be 3y times 4z is going to be 12yz. And now I'm going to do this last one, 4z. 4z times 2x is going to be 8xz. 4z times 3y is going to be 12yz. 4z times 4z is going to be 16z squared. And now let's simplify this. We have a 4x squared. And we have 6xy plus 6xy, that'll give me 12xy. And now I also have, where do I have xz, 8xz. I have an 8xz plus an 8xz here. That'll give me 16xz. I also have a 9y squared plus 12 plus 12yz plus 24yz and a 16z squared. So now we can see that this expanded form is not equal to this, and I can say therefore not equivalent at all. And that's that. So that has been some multiplying of some binomials or trinomials, polynomials overall. If we take it one step at a time and be vigilant and go through this tedious process, we shouldn't have a problem. So yeah, that's all for this video. I'll see you in the next one. Okay, so in this video we're going to be factoring polynomials. So let's start with a function. And now we're going to use a technique called grouping. And this is basically when I take this polynomial and I group it into pairs that I can see are going to give me common factors. So I can see that this multiplied by 3 is that, and that multiplied by 3 is that. So from the first bracket I can factor out, let's see, 3n squared. Actually, sorry, just n squared. squared out from 3n squared, I'm left with 3. And similarly, if I took out a common factor from here, which is 2, obviously, I'm left with n plus 3. And because I'm left with the exact same thing, I can write this out like and then n squared plus 2. And that is how I can factor by grouping. And now let's look at some quadratics. Let's do like a quick refresher. Remember, we want two numbers that multiply to the third term and add up to the second term. And remember the sign of the third term, if it's negative, it means I have a positive multiplying by a negative. So that's the first thing. And it means, well, the negative means that it's two different signs, positive or negative, negative or positive. But to figure out which one or how they multiply or add up, I know that they add up to the middle number, which is if that's also a negative. I know that the bigger number is going to be negative because, let's put it like this, because when you add these two numbers up, you're still in the negative. So in this case, two numbers that add up to 30. I mean, you can do 1 and 30, 2 and 15, 3 and 10, 4, not exactly, but 5 and 6. And the ones that add up to that, to a negative 1, in this case, the only ones off by 1 are these ones. And my bigger number is going to be negative, so I'm going to have x minus 6, x plus 5. So that's what I'm left with. So, let's do another one. Let's do 18x squared minus 50. And let's see where we can take things out. So one of the first things I see, a common denominator between these two, is a 2. I'm left with 9x squared minus 25. And now I can see that 3 squared gives me 9 and 5 squared gives me 5. So there is that rule that we learned in our previous year's lesson, x squared minus y squared equals, well, let me write an easier way. And x squared minus y squared is equal to, well, I forget the exact thing. I'll find it and I'll put it in somewhere. But this eventually will become 3x plus 5, 3x minus 5. So basically this rule is going to be that's the rule. And understanding this, we'll be able to look at something like that and quickly go down into that. So that's something important to have. Let's continue. Let's do another one. Let's do so ways to go about this, but in this case, we're going to do something called, like when we look at this, we see that we don't have any common factors. So what we can do is take this middle term and split it. So I know that 5x minus 6x is equal to negative x. So instead of writing that, I'm just going to write in. And the logic behind knowing when to do this is when, like, you don't have any common factors here, or this doesn't fulfill any identities, then I can do something like this, and then I can group. Again, I can do a 5x, and I'm left with 2x plus 1, and then what can I take out from here? Let's see, negative 3. So if I take out a negative 3, I'm left with 2x plus 1. And again, I'm left with 5x minus 3. And there we go. Now let's do another one. Let's do 9x squared. This one, let's see how we can approach this. I believe this looks like a perfect square. Again, notice the squares always. In the last one we had the, what was it? The 9x squared minus 25, which became x plus y, x minus y. If you remember from our previous year video on perfect squares, there's another rule in which it is x plus y. Oh, let's do an x plus y. Sorry, I believe it was x plus y times x plus y gives me x squared plus 2xy plus y squared. So recognizing that this is actually 3x, and then our y is actually 5. Right, and if I was to expand this, 3 times 3x, 9x squared plus 15x plus 15x plus 25. Yep, and I end up with that. So that is my answer. So actually 3x plus 5 squared. And yeah, we can continue with something maybe a bit more fun. It probably won't be fun, but let's try it. So, let's do what we always do. Let's group. I know that when I have x plus 1 here, nothing to factor out there, but here, if I factor out x squared, I'm left with x plus 1. It looks scary in the beginning, but look how simple it got. Let's what I can do. That doesn't have any common things over there, but I can see this. I know that is one of these. Yeah, that'll give me, one of those. X squared minus 2xy minus y squared, or plus y squared. Negative gives me a positive product. So that should give me, by that logic, x. And then my y in this case is a 3. And now I'm left with 4y squared. But technically, this is that is actually 2y squared. So by the same logic that I used here, let's see if I can do the exact same thing again using difference of squares. If by this logic I do, I should be able to refactor this in. No, hold on. It was actually this one. So that so in this case, this entire term is x and this entire term is y. So if I want to put into this, I can write x, which is x minus 3 plus y. And then the same, x minus 3 minus 2y. And that is how we do difference of squares. So yeah, that has been a little bit of polynomial factoring. And I hope you picked up something from it. And yeah, I shall see you in the next one. Okay, so in this video we're going to be simplifying rational functions. So let's start with the function. And this function, we are going to simplify it so let's see what we can do with this. Let's try simplifying either the numerator or denominator first, or we can actually do it in parallel. So let's look at the numerator. What can I factor out from the top? 3n squared. Right. And from the denominator, I can see that I can factor out a 4n, which will leave me with squared minus n minus 2n. And yeah, that's that. The full way to do this in steps would have been 2n squared minus 2n minus n plus 1. I believe, yeah. No, hold on. Minus... Nope, sorry. Other way around. 2n squared minus n minus 2n plus 1. And then if I factor out a negative 1 from there, yeah, so 2n squared minus n minus 2n plus 1, factoring out an n, so I'm left with 2n minus 1, and then from here I can factor out a negative 1, and I'm left with 2n minus 1 minus 1 and minus 1. That's what you get here. So now I see something clearly in this function, that I have an n minus 1 in the numerator and an n minus 1 in the denominator. These will cancel out, and I'm left with 3n squared over 4n times 2n minus 1. And there we have it. Let's try doing another one. Maybe not in green. Let's try blue. Let's do so let's look at this. Let's see if we can factor out something in both the numerator and denominator to cancel out. I know that I can do this very quickly in my head and write out the final answer, but if we were to do it step by step, I want to basically factor out everything that I can cancel and then cross them out. So I know that something that's common here is going to be a 6 from the numerator. I'm left with 5. I know that I have a common of x4 and a common of 1y. So I'm left with y squared here. And in the denominator I have a negative 6. And if I was going to take out an x4, I'll leave the negative in here. And I also have a y. So if I factor out that from there, the 6 and the x4, I'm left with the negative x cubed. So this will cancel. And I'm left with the negative. And that is that. Let's do another one. Let's do one with, let's do 10x4 minus 8x 4x over 2x squared. So, what's one of the first things I can take out? I know I can factor out 2 and x from the numerator. Oh, that's squared, sorry. So I'm left with 5x cubed Let's look at another one. Let's do maybe red. Let's do this one. X squared plus 7x minus 8 over 2 minus 2x. So from the numerator, I can break this down into two numbers that multiply to negative 8 but add up to that. So I have 1 and 8 that's going to add up to that. So I'll do 8 minus 1, so that's x minus 1, x plus 8. And then in the denominator, I can take out a 2. From here, so I'm left 1 minus 2, 1 minus x, sorry. So I notice one thing. If I take out a negative sign from this right here, I can actually flip the signs inside of it. And I'm left with 1 minus x on the numerator and denominator. And I'm left with negative. Which is also, negative x minus 8 over 2. Maybe we can do one last one. Let's do this one. So let's take out a 4 from the numerator. Let's do that. So this is also just like writing from before. We have x. Remember that? So let's do that. Let's do something with the denominator first. The denominator looks like it's a two numbers that add up to that. I think we can do two numbers that add up to this but multiply to that. Let's see if we can do, because this is technically it's a 1. So if we do add something like x plus y times x minus y, because that's a negative, but this one's going to be positive, so I can do that. 3 times 2, it'll give me a 6. A negative 6. Negative 2y times positive 3y will give me a negative 6y squared. Plus 3xy minus 2xy will give me that. So that should give me and this I can rewrite as the difference of squares formula. It should give me and that will put me here. And now, boom, we have a common term in the numerator and denominator. And now I can write it out as 4 times x minus 2y over x plus 3y. And that's that. That is how we can factor simplify rational equations. So yeah, I hope you enjoyed that or learned something. That's all for this video on simplifying rational functions. I shall see you in the next one. Okay. Okay, so in this video we're going to be multiplying and dividing rational expressions. So let's start with something 6x squared over 5xy times 15x y cubed times x 8xy to the 4. Now, as we remember multiplying fractions, you just go straight across. And so 6 times 5 should give me 90. And then I can add the exponents, so x cubed, and then I have a y cubed. Same with here. 5 times 8 is 40. X to the 1 and x to the 1 will give me x to the 2. Y to the 1 and y to the 4 will give me y to the 5. So now we remember how to factor things out. So I know that 90 over 40 is the same as 9 over 4. And then x to the 3 divided by x to the 2, the exponents will subtract, so I'm left with x to the 1 in the numerator, and then so that'll cancel. I'm left with x. These two will cancel. On the bottom, 3 minus 5 will give me negative 2. So that's basically like saying that, we could have put negative 2 like this, 9x y negative 2 over 4, but this negative 2 just means it's a 1 over y to the 2, so same as this. So yeah, that has been a very simple one. Let's do something a bit more fun. So, right off the bat, let's start doing some factoring. I can factor this and that. I know that that's my difference of squares, so that'll be x minus 2, x plus 2, x plus 6, x plus 6, that's just x plus 6 squared, times, let's factor that out, two numbers that multiply to 18 but add up to 9, same sign. That should be 3 times 6, x plus 3, x plus 6 divided by 2 times, see this 2, x minus 2, if I take out the negative sign from the bracket and put it in front of there, I'm left with x plus 2. Sorry, no, x minus 2. Now, I can start canceling things out. So if I put all this over the same bracket, or the same fraction, now I have in the denominator x minus 2 in the numerator. Those are gone. Same with one of these x plus 6's. And now all I'm left with is that negative in the denominator with that. So I can bring the negative up here. So I can write negative x plus 2. I'm left with this one, x plus 3. And denominator. The 2 is still there. X plus 6. And that was very straightforward. I'm just expanding or factoring and then just doing a little bit of work. Let's do another one. Maybe one more. This one looks like it's gonna be fun. Let's do this one. Let's do. I want to blow this one. Let's go. 21p minus 3p squared over 16p plus 4p squared divided by 14 minus 9p plus p squared 12 plus 7p plus p squared. So now that we have a division sign, that means nothing. All we do is flip the sign. Okay? And then these I'm going to rewrite it in ways that I like. I like putting my higher numbers on one side. So, let's factor out a 3p from here first. Let's do 3p, because I know 21 and 3 have a common factor of 3, so that'll give me 7 minus p. And then for this one, I also have a 4 and a p in both, so I can do and now we're going to flip this around to multiply. So in the numerator, I'm going to have this. But if I was to factor that ahead of time, that's the same as writing this p squared plus 7p plus 12. So two numbers that multiply to 12 and add up to that, that's 3 and 4. So I can write that out. But if I write it out like that, well, let's just write it out like that, see what happens. 4 plus p, 3 plus p. And the same goes for the numerator. That's p squared minus 9p plus 14. So that'll give me two numbers, two negative numbers. I'm going to say negative 2 and negative 7, p and p. Yeah, that should work. 7 minus p, 2 minus p. And right away I can see so many things to cancel. 4 plus p, 4 plus p, 7 minus p, 7 minus p. And so what does that leave me with in the numerator? I have this p here and that p there. So now I'm left with 3 in the numerator with this 3 plus p. And denominator I have a 4 and a 2 minus p. And yeah, that's all it was. Simple as that. Just factoring. When you can factor them, then you can easily just start canceling them out in the numerator and denominators. But yeah, that's been a common theme here that we just kept repeating and repeating. And I hope this next one. Okay, so in this video we're going to be adding and subtracting rational expressions. So, jumping off of what we've been doing so far. We've been simplifying, multiplying, dividing expressions. So now I'm going to take this and add in to all the, I'm going to take these three terms and turn it into one simple term, or like group and everything. You'll see what we do. So, as you can see, we can treat these like fractions. Usually when we add fractions like 1 over 2 plus 1 over 3 plus 1 over 4, we try to find a common denominator between them. And once we have the common denominator, then we can turn it into one simple term. So we're going to do the same here. And we're going to start by finding a common term between these three. And so we know that we have numbers in front of each, like a real value between each one. So let's try to find a common multiple of these three values. So let's do the largest possible number between these, the smallest number that all three of these multiply to. So I know that, let's see, I can't do 12. Let's try 8 plus 8 equals 16. That doesn't go into 16. But 24. So this can multiply by 3 into 24. This can multiply by my math is killing me right now, 6, and this can multiply into 4. So one other thing, we have this x in the denominator. So the lowest common multiple I can do for x in terms of the variable is going to be x cubed. And you'll see why. So this fraction here, I can multiply by 4 over 4, which is basically multiplying it by 1. This middle one I can multiply in order to get, well, this is going to be my lowest common multiple. Let's say lowest common multiple. Now if I want this middle term to become this, the denominator to become that, I have to multiply the denominator by 6x. Because 6 times 4 is going to give 24. X times, wait, I need an x squared to give me x cubed. 6x squared. 6x squared divided by 6x squared. And then this one I can multiply by 3x. That'll give me 24x cubed. So when this multiplies by that, I should get 9x over 24x cubed plus 6x squared over 20x cubed minus 20 over 24x cubed. And now I can put all of them over the same denominator. And there you go. That was much more simpler than this original problem looked. Let's do another one. Something a little more challenging. Let's do 2 plus 1 times, no, sorry, let's do minus 3. So let's say I have this problem now. Our lowest common multiplier, or common factor, or denominator, sorry. Our lowest common denominator in this case is going to be these two multiplied by each other. So, how do we do this? The same as we used to do in fractions, we cross multiply. 3n minus 3 plus 2n plus 1 times 4. And when we multiplied this side by that, by this, our cross multiplication, it's like we're multiplying by 1. And then this side we're going to multiply it by 2n plus 1. And we already had the n minus 3 there. And now this can all go under one common denominator. So it's going to be plus and there we go. Now we can actually start simplifying this by expanding these brackets. So now we can do, we have 3 3n squared, as this multiplies in there, and that's going to multiply in there, minus 9n plus 8n plus 4. And as you can see, we can group these terms and put them together. So we're gonna have 3n squared minus negative 9 plus 8. It's going to be n, which is negative 1 plus 4. And that is my final answer. So we went from this down to this. And yeah, it seems like we're just doing algebra, expanding and simplifying. Let's do one a little bit more complex. Let's do this one. 2t over t squared minus 1 minus t plus 2 over t squared plus 3t minus 4. This is going to be interesting. So, here, I could just cross multiply and simplify. But if I wanted to save myself trouble, I know that this is a difference of squares. T squared minus 1 squared. So that'll give me t minus 1, t plus 1. That's what this is. And this one, I can also factor two numbers that multiply to negative 4 and add up to positive 3. That's t plus 4, t minus 1. So I can rewrite this as 2t over t minus 1, t minus, or t plus 1, subtract t plus 2 over t plus 4 by t plus 1 over t plus 1. And I can multiply this one with what it doesn't have, t plus 4. And now the denominators are going to be the same. You have a t plus 4, a t minus 1, and a t plus 1 in both. So now I can actually start simplifying this. I'll put all of it under one denominator. T plus 4 times 2t, subtract t plus 2, t plus 1. T plus 4, t minus 1, t plus 1. Now that is my expression. Now it's time to do the fun part. And that is to expand everything and simplify. So let's do this. 2t into that. 2t squared plus 8t, which is that one. Now when I open this up, so these are going to be negative 1 times whatever this is. So I know t times t is going to be t squared, but I have the negative in front. So I'm going to put t minus, minus t, and then minus 2t, because of this negative. And then I have 2 times 1, and then the multiplying by the negative, all over t plus 4, t minus 1, t plus 1. And now time to simplify. I got a t squared and a t squared. 2 minus 1, that's just t squared. And then I got 8t minus t minus 2t. So that'll give me 8 minus 1 minus 2. And then I'm just left with my 2. And that is my answer. If you ever are asked to find the restrictions on this, just understand that the denominator cannot be negative. So t in this bracket, t cannot be 1, because if it is 1, this will be 0, and the whole denominator will be 0. 0 times anything is 0. And this one, it cannot be negative 1, and t cannot be negative 4. So yeah, I hope that was helpful, intuitive, or educational to some extent. But yeah, that is all for this video on adding and subtracting rational expressions. And I'll see you in the next confusing video. Okay, so in this video we're going to be looking at the quadratic function and actually we're going to try to apply it to like a real problem. So let's pretend that somebody is standing on a surface here and they throw something down that way, and then it falls like this. So we're going to look at this kind of a problem where we have a falling motion, so a downward parabola. So we know that this object that's being thrown is modeled by this function. height of the tool. And this is t. And t is going to be our time in seconds. And let's call it meters for the height. So, basically, our first question is going to be, how high do we start? If this is our function, how high was it thrown from, our object? And when you get asked that kind of question, how high was it thrown from, you know that it's our starting point. That's here, where t is equal to 0. That's when our object is thrown. Then we model how long it takes to hit the ground. So to find out how high we are above the ground, we're going to just put in 0 into this function. And obviously this is 0, this is 0, and we're left with 25 meters. Now, let's go with another one. Our second part to this question is, when is it going to hit the ground? And the answer to that, you just look at this graph and you kind of just say, okay, when it hits the ground, that means my height, h of t, is equal to 0. So this value is 0, so I can just do that. And these kind of problems come up a lot in physics, but yeah. So now, I have this, and what I could easily do now is factor this out. Let's factor this, what we've been doing for the past several videos. Let's factor out a negative 5. So if I take out a negative 5 from here, because I see it's a common factor, I'm left with a negative 4t and a negative 5. Now I'm left with this, and I could easily factor this down. Two numbers that multiply to negative 5 but add up to negative 4. So negative 5 means opposite signs, so I'm going to have t plus something and t minus something. And since I have a negative middle number, that means the bigger number is going to be a negative. So two numbers that multiply to 5 are 1 and 5, and the difference is going to be negative 4. I can do that. And now I'm left with this. Now, this will give me the roots by saying t plus 1 equals to 0 and t minus 5 equals to 0. So when I solve for this, t is equal to negative 1 or t is equal to 5. The reason for these is because if I was to plug in 5 into here, this will become 0. 5 minus 5 will give me a 0. And the whole thing becomes 0. So that is one solution. And the other one is negative 1. If I plugged into here, it'll give me a 0 for the whole equation. So these two hold true for this, because it's a parabola. But the thing is, time cannot be negative, because we're using a real world problem. So this solution goes out the window. And that is my only good solution here. So now I can conclude that the tool, or this object, will hit the ground after 5 seconds. And let's see, if we were to map this out, another question could be, hey, what is the line of symmetry for this graph, wherever you were to plug it in? And the answer to that is, you take your two, our two solutions, negative 1 and 5, and I basically want to find out, because this is going to be a symmetrical thing, doesn't necessarily have to be right in the dead center. It could have been here. Our h of t and t. Because sometimes you can throw this upwards and it'll fall down. So that's why we have a -1 and a 5. So how do I find my line of symmetry? Basically where it peaks and then comes down. Or the point at which it goes this way and that way. And that's easy. You just take these two, add them, and divide them by 2. So when you add these, you get 4 over 2. You get 2. So that's at 2. And now we know that actually we can do another thing. We could actually plug in this 2 into this equation here, and that'll give me -5 times 2 squared plus 20 times 2 plus 25. That'll give me -20 plus 40 plus 25, 45. That'll give me my root 2, 45. That is where the root is in our graph if we were to graph this out. And yeah, from that we can actually write out the domain. Our domain is going to be basically our x values, so that's going to start from here and go all the way to when it ends. So we're going to have our time is going to be 0 to 5, and our range is going to be, we know that it hits the ground and it maxes out at 45, so that's going to be our range to height. I'm getting bad at writing. It's going to be from 0 to 45. Yep. That is it. So, now let's look at another one. Let's say we have a function. And now I just want to look at the properties. Now here I have it in vertex form. And if you don't understand vertex form, I've made a video on that as well. So, if I wanted to graph this, and keep in mind mine is going to be a very rough sketch, but yeah, let's try it out. The first thing I can do is take the vertex from the vertex form. I know that this value right here and that value will give me the vertex. Because remember, we are going to have a shift whenever we have our graph and we have a negative number here, x minus something. That means we're going to move to the right, not the left. And then we have a -5, which means it's going down 5. So our vertex is going to be 1, 5. Sorry, -5. That's negative. And that means my axis of symmetry, meaning where it opens up. Either it's going like this or like this, whatever. It's going to, our axis of symmetry is going to be at 1. And I know that because this is positive, there has been no reflection on the x-axis, so I know it's going to open upwards. So, based on these things, now I can do one of our favorite things is to find the 0 for x. Because when x is 0, that's when it's going to cross the y-intercept. So if I plug in f of 0, I should get 2 times 0 minus 1 squared minus 5. That will give me 2 times negative 1 squared minus 5. Negative 1 squared is 1 minus 5. I should get 2 minus 5. It's, well, I'll just write it here. Negative 3. So at some point it crosses into the y-intercept at negative 3. So now, based on these things that I have, I can easily just write or graph this out. If I have a 1, 2, 3, 4, 5 to negative 5, I know that negative 3 is where it crosses. I know my root is right there. So yeah, let's see. That is basically a rough sketch of how I can do that. So this is my f of x function roughly sketched. In future video, we might actually convert this into standard form and find the x-intercepts to make sure these are more accurate. But yeah, for now, that is all for this video on the quadratic function. I hope it clarified some stuff, or you learned a little bit. But yeah, that's all for this video. I shall see you in the next one. Okay, so continuing on quadratic functions, in this video we're going to be looking at the max and min of a quadratic function. So given a function, say h of t equals negative 5t squared plus 40t plus 100. Say this represents somebody hitting a golf ball, right? So, say I have a quadratic function that represents this. I want to find out the max point or the max height that this golf ball will hit. And because I have a negative in the start of the function, I know that my parabola is going to open downward somehow. But yeah, what we're going to do in this specific example, we're going to do something called completing the square. And we've covered this in a previous video. So basically it's when I'm going to factor this out here into a bracket. I want to convert this into a vertex form. Right now it's in standard form. And I want to go into vertex, and I'm going to factor out a negative 5 here, so I'm left with t squared minus, if I take a 5 out, minus 8t, and I took a negative out, plus 100. this tells me is if I was to open this up, I will get t squared minus 4t minus 4t plus 16. So t squared minus 8t plus 16. So I have just this much, but I want to turn it into this. And I can't do that without, I can't just add 16. I also have to subtract 16 to make sure I haven't done anything. So me adding 16 there and subtracting 16 there, it's basically this. If you were to solve it, it would be 0. But what I'm going to do is kick this guy out, this negative 16. I'm going to kick him out of this bracket. And I can't just move him out because this bracket is being multiplied by negative 5. So I can do that by doing this. Once I have moved him out, I can basically say because that guy is being multiplied with that, and this is the same as that, because if I was to factor out a negative 5 from both of them, I would end up putting it into the bracket like that and cancelling those out, and I end up back here. So that's as if I didn't do anything. So negative 5. Well, now I can actually write this as what I wanted. And that's plus 80. Yeah, negative 16 times negative 5 is 80. Plus 80. And the 100 over there is going to be plus 180. And there we have it. Now, we're in vertex form, and from vertex form, we can take the root, which is 4, 180. Remember, that's a negative of whatever you see here, because it's t minus h in our formula. And that is covered in a previous video as well as to why I'm taking the negative. But you should know that that is the opposite of whatever that is, and that is as it is. This means I'm going in our original parabola. For one, it's been flipped upside down, and then my root has been moved from if this says minus 4, that means I've moved this way 4 units. And then I've moved also up to 180. So my parabola kind of looks something like this. The root is somewhere there. And I haven't found the x and y intercepts yet, so I can't graph that yet. But my main issue was finding the max. And my max is that the golf ball will go to a maximum of 180. So, let's do the same problem again. Except, instead of using completing the squares, I'm going to do something else, another method. And in this case, I am going to determine the zeros. So I'm going to factor it out. So, as you know, the parabola is going to be shaped something, I don't know exactly what, but if I find out the two zeros, wherever they are, I can find the midpoint, and I can plug that midpoint in to the formula and find out the max y value, or h of t value. So let's do that. I know that I can factor out a negative 5 scales to factor this. Two numbers that multiply to 20 but add up to -8. I'm going to do 10 and 2. And I know that they're going to be negative, or sorry, opposite signs. Because it's my negative third value, but the 10 is going to be negative because it's a bigger one. So the middle number is negative. So now I have this. Now I can plug in 0 for that because I'm going to have a 0 h of t value, or yeah, height. Now let's see what our zeros are going to be. T plus 2 equals 0, which means t is -2. T minus 10 equals 0. T is positive 10. And it cannot be this because our time cannot be negative. So t has to be 10. So let's plug in our 10. Actually, wait, 10 is going to give me that. And I'm going to get 0. I don't want to plug that in. But I do. I completely forgot the point of what I was doing. I want to find the midpoint. And that is going to give me -2 plus 10. 8 over 2 is 4. So that's going to be 4. So now let's plug in 4 and see what our max value is. And as you already know, we do have 4 as our vertex point, our x value. So now let's plug that into this formula. Actually, we can plug it into this one. It's much easier. Or actually, they're all the same. Let's do our factored one. 4 minus 10. 4 plus 2. This should give me -6. That should give me a 6. So 6 times 6 is 36 times 5. So negatives cancel and I'm left with a positive 180. And it's as simple as that. I wonder if I can do one more example. Let's do another one. Let's do p of x equals -6 plus 40. So let's say this represents our price of a product in which we're selling. The selling price. And x is the product number of units. Let's do 6x. So and then let's have another function. We're gonna call this cost. So let's give our cost function a reason to exist. So now we're going to basically want to calculate the maximum number of profits. So as we know, what we're going to do is basically multiply well, let's start with some definitions. I know revenue is our hold on. I'm going to say the demand. P of x is my demand. So times so our revenue is going to be x. So, and our profit is going to be our revenue minus our cost. That's this function. So if we were to write this out, our profit function, our profit of x is going to be this p of x times x, our demand times our units sold, minus our cost function. And when you write it all out, you get negative 6x plus 40 times x minus 4x minus 4 plus 48. So now let's expand this. And if I was to expand it, I should get negative 6x squared plus 40x minus 4x minus 48, which leaves me with this again is a word problem, and solving word problems, it really is just reading the question over and over again, because they never put anything in the word problem that you don't need. Every sentence has some sort of giveaway or hint that you need to use. So let's start working on this. This is standard form, and I want to find the max profit. So I want to find the max point. So let's convert this into our vertex form. The only way, well, we know multiple ways, but from before, we are going to complete so let's factor that out. There's actually a much simpler way to do this. Let's take the, negative 6x. If I was to factor that out from the front, I get x minus 6. And now from here, what can I do? Okay, I have negative 6x, x plus 3. Well, if I was to move that over, okay, I think I could do that. If I move that over, and now I'm oh wait, that makes sense. Okay. If I plug in 6 times 6, 36, 8. Okay. So now, if I plug in 0 here, I should be able to get x equals 0 from this, and x equals 6 from that. And then these 2 points should give me these 2 points. But if I was to plug in this value, to find the point of symmetry, I should get a 3. And if I plug a guys, the question actually says that x is represented in thousands. So $6,000 for 3,000 units sold. But, I like to keep it simple and, well, not that simple, clearly. But yeah, that, I guess, wraps up this video on the min and max of quadratic functions. I hope you got the gist of it. And that's all for this video. I shall see you in the next one. Okay, so in this video, we're gonna look at the inverse of a quadratic function. So, we know that a quadratic function is like this, and we've looked at inverse functions, which basically are reflections above this line here, y equals x. And that's because, we swap these two values when we want to find the inverse of a function. Another thing I should mention, that a function is, well, by definition, a function only has one y value for every x value. So keep that in mind. So we know that this is what our quadratic equation looks like. And if we were to draw that line like that, so let's draw a bigger one. If we were just to do y equals x squared, which is, 0, 0, 1, 1, 1, 2, 4, 3, 9, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7, 8, 9, 0, 0, 1, 1, 1, 2, 3, 4, that's 2, 4, 5, 6, 7, 8, 9, somewhere here. And yeah, you guessed it, that is our function. This is our y equals x squared function. But now, let's say I want to find the inverse function. And that is very simple. I just, my imaginary line, y equals x. And let's draw out the inverse function, which is going to be something like this. So that point will come here. That point will come, that point will come on this. If it's over there, then it's going to come over here. That's going to stay there. That one is going to go 1, 2, 3, 4, 1, 2, 3, 4, right here. And so on and so forth. So that's basically going to become like that. Approximately. So this is going to be our inverse quadratic function. As you can see, well, it is actually not a function, because for every y value I actually have for every x value I have 2 points. So at this point I have 2, this I have 2 anywhere. So that's why from our mathematical logic, our vertical line test, the inverse of a quadratic function is not a function. is, as we always do, let's look at the domain. So the domain for this original quadratic function, this will go indefinitely that way and that way, so it's x all real numbers, but on our inverse one, we see x starts at 0 and goes all the way to infinity. So that's our, and then our domain. And then our range, meaning our y values, in this case now, is YER, because it's going to go indefinitely that way and that way, both in the positive and the negative direction. And that's funny because before, for our quadratic, we had, it was the opposite. So we had all x and then y greater, or sorry, and now it's flipped. So there's that. But enough of the background information. Let's actually look at a real example. So I'm going to take a quadratic function, say and say I want to graph it, right? Let's draw a rough sketch. So I have a point, our vertex format, I can take that point, -3, -4, about there, and say it goes like that. And then, like, if I was to draw the inverse, that would be something like, something like that. So let's look at, or let's try to figure out the actual equation of the inverse of x. So what we're going to do is take our original function f of x, and now we're going to swap the x and y. We'll write it out first. Y equals 2, x plus 3, minus 4. Let's swap the x and the y. And now I want to rearrange this in terms of y. So first thing I'm going to do is, I have a -4. I'm going to add 4. So I have x plus 4 equals 2. Y plus 3 squared. I have a 2 here, so we'll divide both sides by 2. And now I'm left with x plus 4 over 2. Y plus 3 squared. To get rid of the squared, I'll just square root both sides. And now I'm left with y plus 3 and x plus 4 over 2. And now, one thing I should mention is when you do a square root, you can get either a positive or a negative number, because when you square something, any positive number, if you square a positive number, you get a positive number. But if you square a negative number, you also get a positive number. inverse is very straightforward. Maybe we can do one more. Just finding the inverse, just so we can nail it in f of x equals negative 2x plus 1 squared plus 4. Now again, let's swap the x and the y, so x equals negative 2, y plus 1 squared plus 4. Let's get to the 4 first, x minus 4 equals negative 2, y plus 1. Let's do the negative 2. I'm just going to swap the sides. That's still a squared. Let's square root both sides and left with y plus 1 equals. And now I have the 1, so just move that over. And one thing I should mention, this plus or minus, this actually equates to me writing this out. Sorry. Minus. So I have 2, and that is because, remember, our inverse function at any given x, I have 2 points at any, except for the origin, or like the root. That's why I have 2 points, 1 plus, 1 minus. And yeah, that's the magic behind the inverse of a quadratic function. I hope that this has been helpful in some sort of way. And yeah, I shall see you in our next math video. Okay, so in this video, we're going to look at radicals. So a radical is basically a square or a cube or a higher root, such as like, let's see, root 4 is a radical, but that is equal to 2, or cube root of 27, which is 3, 3 times 3 times 3, 3 times 3 is 9, times 3 is 27. So this is called the radical symbol, and it's a way to represent numbers without having to deal with all the little fractions or decimal points. It's easier to do like math or like simplification with radicals. So another thing, some terminology, an entire radical is a radical with a coefficient of 1. So something that's like, say that, there's like a 1 in front of it, but you don't write it, you just write like that or that. And a mixed radical is going to be something that has a coefficient like that, or let's do 5 root 6, like, and we're going to learn how we can actually do radical math. So for example, let's say I have root 72, and now I want to take this and express it in as a mixed radical, because this is an entire radical. I want to express this as a mixed radical in its lowest possible terms. So I can say that 72, the square root of 72, is equal to the square root of 36 times the square root of 2. And this is true because if I do 70, square root is basically to the power of negative 1 over 2, right? And like, as we know from like our videos on exponent math, you can do, well, not negative, sorry, that's not negative, it's just 1 over 2. It really is just 1 over 2, so 72 to the power of 0.5 is equal to 36 to the power of 0.5 times 2 to the power of 0.5. And like, this becomes, okay, so that comes from our exponent laws. So when we're dealing with radicals and you want to break this down, I know that 2 times 36 is that, and I know that 36 can easily become a 6. And boom, instead of writing root 72, I have such a smaller number, simpler number to represent it with. And you know what? Let's do another one. Let's do 5 root 27. And I know that this is the equivalent of saying 5 times the root of. Let's try to find a number or two numbers that multiply to 27. But one of those numbers are going to be something that I can square root perfectly. And so well, I know that 9 times 3 is 27. And I know that 9 is 3 squared. So I can write it like that. 5 times root 9 times root 3. That's the same as writing 5 times the square root of 9 is 3 times root 3. And now my 5 times 3 is 15. And I'm left with the root 3. So now I have 5 root 27 is the same as that. And you can punch that into a calculator. Similarly, we can go the other way. As I'm breaking this down into smaller ones, or into mixed radicals, I can go the other way. Take this and convert it into that, into entire radicals. So, let's say I have one. Say I want to take 4 root 5, and I want to say this is the same as writing 4 times root 5, but 4 is also the same as writing root 16, and I can do that. And when I put these two together from my exponent law, 16 times 5, there you go. Boom. And let's do another one. Let's do negative 6 root 3. Negative 6 root 3 is like saying negative 6 times negative 6 times root 3. But one thing to be careful with, you don't want to put a negative number under the square root. So let's just take that out. And now I have 6. And I have... Now let's write 6 as... But I still get into the more fun stuff where we want to, say for example, simplify. Say I have root 5 times root 11. Well, that's a very easy one. I don't know why I was even giving you that one. You just do what we've been doing here. 5 times 11 root 55. Okay, let's forget I did that one. Let's do something a bit more complex. Let's do something like right here. Negative 4 root 6 times 2 root 6. Say I have this and I want to multiply them. So when you want to multiply these, just write it out as negative 4. Remember, these numbers, the whole numbers, will multiply by each other, and these two will multiply by each other. So I have negative 4 times 2 times root 6 times root 6. So that's negative 8, and those two will give me root 36. Oh wait, root 36, I can turn that into 6, which is negative, forgot the negative, negative 48. So this is the same as this, and that is that. So let's do something more fun now. Let's do addition. I don't know. Let's try it out. Why not? Maybe you're not ready, but maybe you are. So let's say we want to add radicals. So you can't just add any radical, right? You have to add something called like radicals. And this means like things that have the same root numbers under them. So whatever this value under the root is. So you can add like root 3 plus root 3. But if you try to add root 3 plus root 8, you're not gonna get, root 5. If you try to add root 3 to root 5, you will not get root 8. That does not work. So don't try that. But one thing you can look at it like is like root 2 plus root 2 plus root 2. This is equal to root 3 root 2. Root 2. So I have 1 plus 1 plus 1. I can add these ones because they have similar ones. And if I was to take root 3 root 2 and add another root 2, I do get 4 root 2. And yeah, I guess I could, root that again. But yeah, that is something you want to be careful with. So let's do one last example. Say I have a word problem, like this. Say I have this polygon, and these are the lengths of the sides. And now I want to find the perimeter. So the perimeter is, I just add up all the sides. So I just write P is equal to root 8 plus 2 root 3 plus root 12 plus root 18. But remember, I cannot add all these up because I need them to have like, I can only add like radicals. So if you guess that we're going to convert these into something that they're commonly or common radicals, then Yeah, you'd be right. Okay. So this first one, I know I can break that down. I can turn root 8 into 2 times 4, because 4 is something that I can square, or take the square root of, sorry. So that's root 4 times root 2 plus, that's already at its lowest, I can't do anything there. I think I can do something with 12. Again, 4 is something I can do. 4 times 3, I can break that down. And what about this one? A multiple of something that I can square, things that I can square. 1, 2, 3, 4. Sorry, wait. I can square all those. I want to take a perfect square root of, well, there's no point in using 1 as a perfect square root. That'll give me 1. I know I can take the square root of 4. I can take the square root of 9. I can take the square root of 16. So I know 18 gets divided by 9. So that'll be root 9, root 2. So this should give me 2 root 2 plus 2 root 3. This one will give me 2 root 3 plus 3 root 2. So now I have this and this are the same. This one and that one. I can add those ones, so 3 plus 2 is 5 root 2. And I have now this one and this one. 2 plus 2. And boom, there is my perimeter. Now let's do one last one. The other side. I wonder if that's gonna be a problem. Everything gets recycled. Let's do one last thing that we should cover, just so I don't have to do another video on it, is multiplying radicals. 3 minus root 6 times 2 plus now let's multiply these the same way we would binomials. Let's multiply that. 3 times 2 is 6. And then 3 times root 24 is that. And now let's do this. Minus 2 root 6 minus 6 times 24. 144. Okay, well, that works out because that's 12. Okay, that's good, that's good. Okay, so I have 6, and then I have this. I have 2 root 6, which I can't break down, but I think I can break down this one. I can put a 4 and a 6, so 3 times root 4 times root 6. So that's going to become a 2 equals 6 plus 3 times 2 root 6 minus 2 root 6. So that'll give me, let me just put that over there. Now I have plus 6 root 6 minus so in this video we're going to be solving quadratic equations, something that we love now and know how to do. So let's say I have this function, or this quadratic equation, and this is basically representing a balloon that is going to be slowly falling from the top of a building downwards, and it's modeled like this. So t is seconds and h is height in meters. So one of the first things I want to do is find the domain and range of this function, not because I want to, but because I've been asked to on a test or something. So one of the easiest ways to do this is to basically take it. Right now it's sorry, this is going to be my step 2. The actual problem is this. That's the problem. I want to take this from standard form and go into vertex. And that's the step that you gotta do next, because yes, we are completing the square. So an easy way to do this is divide this by 2 and just square it. So t squared minus 6t plus negative 6 over 2 is negative 3 squared is going to be 9. Right? So plus 9 minus 9. I have my negative 5 and I have my 10. And now I'm going to take that negative 9 out, so I'm going to maybe add negative 5 t. Well, let's just write that out. T minus 3 squared. Negative 9 plus, times negative 5. That's going to give me plus 45 plus 10. So now I'm left with now I have my vertex. So domain and range, I know that it's going to point downwards, and my point on this graph is going to be 3 over and plus 55. So 3 comma 55 is my point. So my x range is going to be in this specific word problem, I cannot have a negative time, so it's going to be time er, but time greater or equal to 0. And then we also have our range, which is our h of t. It's all real numbers, but my maximum point on a downward opening parabola is 55. So that means it will not go higher than 55, so h of t will only be less or equal to 55. That's my range, my domain. And that is the domain and range for this. But now let's go with part 2 of this question. When will the height be 30? And that's easy. I just plug in 30 into this formula, negative 5. And I solve. I'll take the 55 out from both sides. And then I should be able to get hold on. Nope, I don't want to do that. That is not the best way to go about this. I should use the quadratic formula. This is a quadratic function. into my quadratic formula. I got my negative b plus or minus square root of b squared minus 4ac, which is 30 squared minus 4 times a, negative 5 times c, all over 2a. So if we were to do that, 900, I believe, minus, oh no, 3 times 3, yeah, oh no, wait, my BC is negative, sorry, so that should give me a negative number. 4 times 5 is 20, 20 times 20 is 400, 900 minus 400 is 500. So now I'm left with well, the root of 500 is approximately 22.36. So I'm gonna do negative 30 plus 22.36 over negative 10, and I'm also gonna do t equals negative 30 minus 22.36 over negative 10, and that is going to give me one of them is going to give me 0.764 and the other one is going to give me 5.236. That means approx. So I have two positive timestamps at which I'm going to get a height of 30 meters. So it means it's gonna do something like that, and 30, it might be somewhere there, somewhere really close to 0 in terms of time. That's 30. It's gonna hit it at 2 points at 2 different times. It's gonna go up and down, and the vertex is somewhere there. So let's do another word problem. Let's say I have some land that is 80 meters by 60 meters. And let's say that I have inside this land, I want to build a factory, and I want the lawn around it, my space around the factory, to be the same on all sides. Okay, so I want like the distance from here to here to be x, the same as this distance, the same as this distance, the same as this distance. So now I'm going to try to solve for the length of this strip of land, or the thing, how wide this lawn is, and I also want the dimensions of this factory. I want to solve for that. I know this is 80, and I'm going to subtract x from this side, x from that side, so the factory is going to be 80 minus 2x on that side, and then 60 minus 2x on this side, because this is 60, and I'm minusing x here and x here. So now we can find out the actual dimensions of the factory. Well, I have the dimensions here. This is going to be the dimensions. expansion. So if I was to expand this binomial, I should get a equals 80 times 6 is 48, so 4800 minus 120x minus 160x minus 4x or plus 4x squared. And that'll give me the area formula of 4800 minus 280x plus 4x squared. And now the area of the lawn is going to be the total area. So 80 times 60 is so my lawn area is going to be like this part here. That's going to be the total area minus my factory area, which is going to be 4800 minus that formula. So it's going to be minus 4800 plus 280x minus 4x squared. So that'll cancel out, and I'm just left with negative 4x squared plus 280x. And now I can see that my formula for the area of the lawn is going to be similar, or when I subtract that from the total area that I have available. Now I have two formulas. I know that from my word problem, the area of the grass, this area, is going to be the same as this one. That is given to me in the problem statement. May have missed it earlier in mentioning that. But now I actually have the area of the lawn and the area of the factory, and I know that they're going to be the same, so I can actually just put them equal to each other. And now, you guessed it, I'm going to move everything over to one side. I'm going to take all these values and put them on that side. So plus 4x, I'm going to subtract from this side 4x squared. That's an x as well. And then the 280, I'm going to add here. The negative 280, I'm going to add it here. So plus 560 x. And then I have the plus 4800. I'm going to subtract the 4800. And now I have this. So I could very easily just factor out 8, negative 8. I'm left with x squared minus 56 over 8, so 70 x. 8 over 48 should give me 6, I believe. Yeah, so 600. So now I can factor this out, and it's easier to do it if you just look at it with like one less zero. But yeah, so we can do 6 and 10 and turn that into 60 and 6 and, well, you get the point. So I'm going to have x, well, they're going to be the same sign, so x minus, so two numbers that multiply to that, but add up to that, I'll do 60 and 10, 600 and dimensions, so x equals 10. That is what our value is going to be. And to solve our initial problem, the dimensions of our factory, 80 minus 2x, which is 80 minus 20, so 60. And then 60 minus 2x, which is 40. So 60 meters by 40 meters. And that is us using quadratics to solve problems in the real world. So I hope you enjoyed that. And yeah, I shall see you in the next one. Okay, so in this video we're going to be looking at the zeros of a quadratic function. So, say we have a quadratic function. The zeros are where it crosses the x-axis. So, those are what we're going to be looking for when we're asked to find the zeros of a function. So, let's say we have a function negative 2x squared plus 12x minus 18. And now, from our previous videos where we've done all our factoring and whatnot, now we're going to look at this in that perspective where I'm going to factor this out, and then you'll see what I do there. So let's just factor this out. I'm taking the negative 2 out of everything, so I'll have 9 here. And now I have this, and I can see that this is a square, a perfect square, so that's x minus 3 squared. And basically, what I want to do is set this equal to 0, because where this will pass by, or where this will go through the x-axis, the x-intercepts, y is 0. So if I set this to 0, basically I have this, well, x minus 3 equal to 0. And now I can just say x is 3, because when x is 3, this equation will be satisfied. 0 will be 0. So I know that this particular function will have something like this. Oh, I know it's a negative 2, so somewhere at negative 2. Hold on, sorry. At 3. Somewhere at 3. When I see it's a negative in the front, or it's a negative function, I know it's opening downwards. So actually I can't assume that this is standard form. I have to look at it in vertex form to make that assumption. So this could be at 3 going up or down. I won't know the exact direction until I put it into vertex form. But most likely it's this, meaning that the point, the root, is going to be at 3. That's where it's going to touch the x-intercept. Meaning there's only one solution, because typically parabolas will have 1, 2, or even none. It can start here and go up. This says 2, this says 1, this says, oh sorry, this says 0. That's 2, 1, 2, 0. So let's look at another one where we have maybe 2 zeros. So let's do g of x. And now let's put it into, let's factor everything and equal it to 0. this one will be if x is 1. So my two zeros are at -4 and 1. Let's do another one. Let's do another one. F of x equal to x squared minus 4x plus 7. So now we can do, let's see, how can I go about this? I can do two numbers that multiply to 7 and add up to 4. I don't think I have anything 1 or 7. Yeah, I don't got anything. So let's take the standard form and change it into vertex form by completing the square. And if you remember, I'm going to take this part right here. I'm going to keep that outside. I want to find a number that adds up to this, but also multiplies by itself. So the easy way to do that is take this middle number here, or this supposed number, so -4. I'm going to divide it by 2 and square it. That'll give me 4. Because then I can do, because with this divided by 2, I'll get 2. So 2 squared. So at that point I'll have x squared minus 4x plus 4, which is x minus 2 squared. That's why it's easy to do that. So I'll have plus 4. Also minus 4, because I don't want to change this equation in any way. I want it to stay the same. If I just add the 4, then it becomes another problem altogether, or another graph. But if I add 4 and subtract 4, I haven't done anything to the equation, technically. But now I want to move this guy out of this bracket. And I have a 1 being multiplied by this bracket, so it's just being multiplied by 1. If I had another number there to take that out, I'd have to multiply that. But here I don't. So now I have this will become that x minus 2 squared plus -4 plus 7, 3. So as you can see, I have this graph. If I was to make this, my root is at 2, 3, and it's opening upwards because I have a positive constant at the beginning. It's a positive 1. So I have nothing touching the x-axis, so no roots. So another thing we can do, say I wanted to do these exact ones again. Say I wanted to plug this in. Another method that I could do this, I factored and I found x equals 3. But another thing I could do, I have, let's see, this standard form, b equals -2, b equals 12. Another thing I could do is put this into my quadratic equation, which is so if I was to plug these numbers in, -b plus or minus square root of 12 squared minus 4 times this part right here is going to give us, and remember, this b squared minus 4ac, that's the discriminant value. Whenever, I've covered this in a previous video, whenever the discriminant is 0, then you have one root. If it's negative, then you have no roots. If it's positive, then you have 2 roots. But here it's 0, so the square root of 0 is 0, so I'm just left with negative 12 over 2 times negative 2, so that's negative 4, and that'll give me 3. Same as the value I got before. And now let's do the second example, or that second one, where I had 2x squared plus 6x minus 8. If I was to plug this in, a equals 2, b equals 6, c equals negative 8, into my quadratic, x equals negative b plus or minus square root of the discriminant. Let's plug it in. You have negative 6 plus or minus 6 squared minus 4 times 2 times negative 8. This is going to be negative 8 times 2, which is 16. 16 times 4 is 64. So that's going to give me a positive negative 4. Negative times a negative. But yeah, 2 times 2, and I'm left with negative 6 plus or minus 36 plus 64. And the denominator is 4. So that'll leave me with 36, 64 is 100. Over 4. So now I have 2. I can go negative 6 plus, well, square root of 100 is 10. And then I can also go negative 6 minus 10 over 4. So plus 10 will give me 4 over 4, which is 1. And then minus will give me negative 16 over 4, which will give me negative 4. And that's exactly what we got before. 1 and 4. Sorry, 1 and negative 4. 1 and negative 4. And even for our other one, we got 3. And here we also have 3. So yeah, the quadratic equation is being proven useful. And the other one where we had no roots, x squared plus 7. If we were to plug that in, let's do negative b. So negative, b is a equals 1, b equals negative 4, c equals 7. Negative b will be not negative b, will be positive 4 plus or minus the square root of b squared plus 4ac, so negative 4 squared minus 4 times 8 and times c all over 2, because 2 times 1, yeah, so 2. I don't even have to solve most of it because I know that I can see that this discriminant right here is going to be 16 minus 4 times 7, 28, and that's going to be negative 12. When that is negative, I have no roots because I'm going to get an imaginary number, and we'll learn about imaginary numbers in the future. So experiments are very easy to use and find like shortcuts to how many roots there are, instead of if you just want to know how many there are very quickly. But another thing we can do is use the discriminant. Like say we have this function. Say this value is a number that's not defined yet. We want to find out what k is. And let's say I want this function to have only one root. So I need to find k so that this function only has one root. And if we use our quadratic formula, a equals 1, b equals k, c equals 3, we can use our discriminant to say that our discriminant, remember, when it's equal to 0, that means we have one root. So I can do k squared minus 4 times 1 times 3 equal to 0. So if I move this stuff over, k squared equals 4 times 1 times 3. K squared equals 12. So now I can do k equals the square root of 12. Actually, plus or minus. K could actually be, because it's getting squared here, so even a negative b of the same value could, like, when squared, it could make this equation equal to 0. So plus or minus. And from our radicals video, we remember how to break this down. Plus or minus 4. And there you go. That is how we can use discriminants to find the number of roots, and also the quadratic formula, and how we can find the actual values of the roots where they hit the intercepts. But yeah, that is all for this video on zeros of a quadratic function. I shall see you in the next one. Okay, so in this video we're going to be learning about linear and quadratic systems. So what this means is, linear obviously means a straight line. Quadratic, as we know it, are curvy stuffs. So we're going to be looking at a problem. Let's say some guy wants to do skydiving, right? So this person is going to be free falling from the airplane, and that is going to be represented by the function h1 of t equals negative 4.9 t squared plus 5500. And t is seconds, and h is height above the ground in meters. So at some point he's going to release his parachute. At this point, h of 2 of t is going to represent his height. So his fall is going to be something like this. It's going to start off very quickly, but then at some point it's going to become linear. So that's just a rough sketch, but what this problem is basically trying to introduce is when quadratics say, a parabola at some point meets a linear function, a line, and they're going to touch at some point, or maybe even at 2 points. But here we're going to focus on the problem at hand. So let's look at this. At some point, these two functions are going to intersect, and that means at that point these two will be the exact same. So what we want to find out is when this parachute will open according to these two functions. So we know that they're going to be equal to each other at some point. So let's represent that mathematically. And now let's just start solving this like a quadratic equation. So let's move everything from here over to that side. That should be 1000. So now I have this. Now let's plug it into our quadratic equation. Oh my God. I'm asleep right now. So we have our A. So let's plug these in. Negative B plus or minus B squared 5 squared minus 4 times 4.9 times C, which is 1000. So negative negative will become a positive, so that's going to be a positive discriminant. I'm good there. So 2A is going to be 2 times negative 4.9, which is negative 9.8, which is actually gravity, 9.8 meters per second squared. That'll come maybe if I do a physics video in the future, but just a fun fact. 25 plus negative 4.9 times 4, it'll give me 19.6. 19.6 times 1000 should give me 19,600. 25. And now I'm left with 5 plus or minus, negative 5 plus or minus 19,625 over negative 9.8. So now I have negative 5 plus the square root, 19,625, and this should give me, this will give me a very, very negative, no, hold on. This will give me a negative number, about negative 13.7. And then this should give me positive 14.8. And remember, I used x here, but it's actually t, so we're solving for t. So we can't have negative 13.7 14.78 seconds. That does not make sense, so it has to be this one. So, at 14.8 seconds after his free fall, he opens his parachute and goes into this linear drop. So, now we can actually plug in 14.8 into this function here. And actually find out that at 14.26 meters, that's how high he was when he opened his parachute. So, that's a little bit of a word problem for you. Let's do a more straightforward problem where I have plus 12x plus 14 and g of x equals 2x minus 8. I want to find the point of intersection, or points, of these two functions. So again, what I'm going to do is at some point these two are going to have the same f of x value. 2x minus 8. Let's bring them all over to the left side. 3x squared plus 10x plus 12 minus 2. And then the 14 plus 8, that should give me 22, equals 0. So, let's plug this into our, so I have a equals 3, b equals 10, equals 22, and if I was to negative 10 plus or minus square root of 10 squared minus 4 times 3 times 22. Okay, that looks problematic already. Hold on, that's going to be 100 minus 4 times 3, 12 times 22. That looks like it's going to be 264. And that's going to give me negative 164. So a negative discriminant means no roots, which means this line and that parabola do not intersect at 0 points Well, that was easy. Let's see. Maybe I can do another one. Let's see. Let's do H of T. Now again, I have a parabola and a line. So let's see if this one is going to So, in actuality, this problem was actually a word problem where this models basically a ball that is being thrown, and then at some point it's going to hit something else, another ball. So a ball's being tossed, and then someone's shooting it with a bullet. So they want to know when these two are going to hit. So, as we can see, or this word problem, t is seconds. So again, our negative second answer is going to be ruled out. And we have a 0.5 answer, 0.5 seconds. And we could easily plug this back into here. So if you plug 0.5 back into here, so that's just 31.5 over 2 plus 1, you'll get 16.75 as your answer. So technically the coordinate at which these two will intersect is on this graph. If you were to graph it out, that's the point of intersection for both the x and the y value. So yeah, a linear function and a quadratic function, they can intersect, but only a maximum of 2 times, no more than 2. So we know that we can use our quadratic function to solve for this. So you should be good to go, good to do this on your own in the real world. So yeah, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be doing a quick wrap or a recap on integer exponents. So because this is going to be useful in the upcoming videos, so a quick reminder. Say we have an exponent b to the negative n. This is equivalent to b to the power of, 1 over bn. That's what the negative exponent is. And b cannot be 0. So, another thing, just some rules. A over b the power of negative n is the same, based off this logic, is 1 over a over n, a over b to the power of positive n, and 1 over that is just b over a to the power of n. And that's also where a and b cannot be cannot be 0. And also, keep this in mind, anything to the power of 0 is automatically 1, and b cannot equal 0. And that actually, we can actually prove really quickly. Say we have 10 to the power of 6 divided by 10 to the power of 6. When you do division, exponent division, so anything over itself, like 1 over 1 is 1, 2 over 2 is 1, 3 over 3 is 1. So 10 to the power of 6 to 10 to the power of 6 is also 1. But if you were to write this out, 10 to the power of 6 minus 6, which is 10 to the 0, you already know this is 1, so it's 1. You could replace this base and this exponent with anything, and you'll end up through this logic equaling 1. this. What else? Yes, so we have the exponent multiplication, b to the power of m, b to the n, and that'll give me b times m times n. I wrote that wrong. So when we're multiplying exponents, we add the exponents, same base. And then same with b to the m over b to the n. We get b to the m minus n. Remember that one too. And also, that's multiplying, dividing, and then we also have b of m, b to the power of m to the power of n is equal to b times m times n. So that'll just multiply inwards. Okay. Forget about that one. So, let us look at some, I guess, ways we could find these things useful. Let me just give myself some space here. So say I had 5 to the negative 3. That from our previous understanding is 1 over 5 to the 3, which is 1 over 5 times 5 times 5, which is 125. And there you go. That's what that is equal to. And if we do, say, negative 4 to the power of negative 2, that is equal to 1 over negative 4 squared, which is equal to 1 over negative 4 squared is positive 16. And then let's do negative 3 to the power of negative 4. That is another ways that we could write it if you didn't want to take the negative downwards. Actually, wait. I wrote this wrong. In this case, I have the negative 4 in a bracket, but here I have the whole expression as a negative, so no bracket. So here, it's like this, technically, but imagine there's no brackets. So here it'll go positive 4, which is the same as writing. Let's do something like this. 2 over 3 to the power of negative 3. And as we remember from doing so many of these, that is the same as I can flip this fraction, or I can evaluate it right now. So this will go into here. Two times 2 is 8 over. And then when you flip that fraction, because that's the base, so this is the logic here. If you were to write out every step, let us do one more. Let's do and denominator we still have 3, and then the negative 3 times 2, so negative 6. And there we have same base. Now we're dividing. So we're left with 3, and when we divide, we subtract. So that'll leave me with 3 subtracting negative 6, so 3 plus 6. 3 to the 9, which is the same as saying I did not do this in my head. I had a calculator. So that is some integer exponent recap for us, which will be useful for us in the future. So come up to speed with these things. And we will work off of this when we look at things like exponential decay or profit interest growth or whatever. But yeah, stay tuned, and I shall see you in the next one. Okay, so in this video we're going to be looking at rational exponents, and so we're hoping in this investigation we're going to basically try to use rational exponents and evaluate expressions containing them. So the first thing we're going to look at is this cube, in case it wasn't obvious. So the volume of a cube can be represented by saying x cubed, and the area of one of its sides can be x squared. You know, x times x, and x times x is the volume. So what we want to do here is basically, from our exponent logic and everything we know about exponents, is represent x in the form, or like as a expression of its volume or its area. So let's just try one. I know a equals x squared. So I basically want to represent x in a way, or like isolate x and represent x in the form of a. So one thing we can do is basically, the quick way to do this would be to square root both sides, and you're left with x equals the square root of a, which is also x to the power of 1 over 2, right? But if you wanted to do the full algebraic way, here's how you would do it. You can say x equals to a to the power of n, and I don't know what n is yet, but I know that a is equal to x times x, which, so by this logic, if a of n equals x, and I have a equals x times x, so that means a is equal to a of n times a of n, a to the power of n times a to the power of n. And our exponent laws tell us that we're going to multiply. Sorry, when we're multiplying exponents, we add them. So it's going to be n plus n, which is also a to the power of 2n. Therefore, I can say that on this side, when we have 1, a to the power of 1 equals a to the power of 2n. Now I'm left with this expression. So with 1 on one side and 2n on the other side, I can write this isolate for n here. So if 1 equals 2n, that means n equals 1 over 2 if I divide both sides by 2. And therefore, x is equal to a to the power of 1 over 2. Oh yeah, sorry. That might have confused somebody. Somebody was confused. And that is the same as writing that square root is basically saying to the power of half. And you know what? Let's look at the volume now. If we were to do it with the volume, so x is equal to v to the power of n, and I know that v is equal to x times x times x, and if each x is v to the n, that's the same as writing v to the power of n plus n, which is, and again I have 1 equals 3n, so n is equal, therefore x is equal to v to the power of 1 over 3, or cube root of v. This is the wrong way to do it, but the correct way, as you see here. But eventually, as you continuously do these problems, you'll see that very quickly when you have, say, v equals x to the power of 4, you can just say, oh, I'm gonna do, when you want to bring this over to the other side, it becomes 1 over 4 equals x. It's very intuitive, like you'll get into the habit of doing it. So let's do some problems. Let's say I have, and I want to evaluate this in radical notation. And if you remember radicals, well, you obviously do remember it. So let's use our exponent logic. So we remember this is 1 over 49 to the positive 1 over 2. And, 49 to the power of half is the same as, say, root 49, which is 1 over 7. Simple as that. Let's do this one. Negative 8 to the power of 1 over 3. You remember how to do that. We have 1 over 3 is the same as our cube root. And we know that we're going to end up with negative 2. One thing that's very tricky here, that you have to wrap your head around is you can take the square root of a positive number. So you can do of any positive number, and you end up with a positive or a negative number. That's fine. But a cube root, if you try taking the square root of a negative number, you're going to end up with an imaginary number. So that's something that we're going to learn much, much later. But yeah, keep that in mind. And when you do cube root, whatever the sign is, it's going to stick. So if you take the cube root of a positive number, you can end up with a positive number. If you do cube root of a negative number, you're going to end up with a negative number. And that is because, say in this case, we have a negative 2, right? Negative 2 cubed is basically basically negative 2 times negative 2 times negative 2. This times that will give me a positive 4. But I'm multiplying it by a negative 2 again, so I'm going to end up with a negative 8. So cube root of this will give me a negative 2. So remember that. And that goes for every odd root that you want to do. So even if you were to do a 5, you end up with the same sign. So yeah, keep that in mind. Let's see if I can get another one in. Say 10,000 to the power of 1 over 4. Let's do a fourth, 10,000 to the power of 1 over 4. That'll give me quad root. And so, basically, do I have a number that will go multiply itself 4 times and give me 10,000? So, let's look at this. I believe it's 10. 10 times 10, it gives me 100. 10 times 10 times 10 give me 1,000. And then another 10 will give me 10,000. Okay. I still got it. Let's look at just this one here. Say we have 27 to the power of 2 over 3. So, let's look at that. Let's break this down first. 27. I have this. 27 is also the same as saying to the power of 1 over 3 times 2. So, if I was to break this down, then I could break this into a power of a power. So I'm left with 27 squared, like that. So that expression here will give me 27 squared cube root. Alternatively, I could go the other way. I could leave 27 here and do the cube root and then square it, which is and I think this is easier than that. 27 squared is a huge number, which is 729, and that'll give me 9. But here, cube root of 27 is 3. So, same. I'm good there. I wonder. Let's try some more. Just to kick this into our habit. Maybe time for a solid color change. Let's do negative 27 to the power of 4 over 3. And we're going to break that down again. Times 4. So that'll give me that's going to be negative 27 cube root 3 times negative 3 times negative 3. These two will multiply and give me a positive. Then I'm going to multiply into this negative and give me a negative. Negative times this negative is going to give me a positive. So the even amounts of times that I'm multiplying this value is going to give me a positive, and odd number amount of times is going to leave me with a negative. Let's do another one. Let's do 16 to the power of negative 0.75. You have to recognize that that's a fraction that I can represent negative 3 over 4, which is the same as saying 1 over 16 3 over 4, which is also the same as saying and I know that that is going to give me a 2. Let me put that on the outside. So let me write it here. So that should give me 1 over 2 cubed, 1 over 8. Yep. I agree. This is very easy. Let's do maybe something a little more complicated. Let's do 8 to the power of 5 over 6 times square root of 8 over 8 to the power of 5 over 3. So let's take this step by step. First off, 8 to the power of 5 over 6. That's 1. That 8 is to the power of half. That one is okay. So, multiplying exponents, let's add them. So, we're going to add the two fractions. 1 over 2 is the same. Let's write that out. 1 over 2 is the same as adding 3 over 6. Wait, did I get that correctly? 1 over 2. Wait, what is that? 5 over 6 plus 1 over 2 is the same as 5 over 6 plus 3 over 6, which is 8 over 6. Okay, 8 over 6 is going to give me 4 over 3. Okay, that's what I want. Over. So now I have this evaluates to 4 over 3. So I have 8 to the power of 4 over 3 divided by 8 to the power of 5 over 3. Dividing exponents is going to give me a subtraction of the exponents, so 4 over 3 minus 5 over 3. So I'm left with 8, I'm left with negative 1 over 3, which is the same as saying 1 over 8 to the power of 1 over 3, which is the same as saying 1 over cube root of 8, which is 1 over 2. Wow. All that evaluated to 1 over 2. Yep, I deserve a break. So, that has been some rational exponents for us. I hope I didn't lose anybody anywhere. But yeah, hope you enjoyed that. And I shall see you in our next video. Okay, So in this video I'm going to be simplifying algebraic expressions involving exponents. So let's look at a sphere that looked like a head, but no, it's a sphere. So let's look at the formulas for a sphere. The surface area of a sphere is 4 pi r squared, and the volume of a sphere is 4 over 3 pi r cubed. So now I want to do this. I want to find this expression, surface area over volume. This basically represents the surface area to volume ratio, in which, well, you'll see what we do. But the point of this being is that we have exponents in this expression, and now I want to simplify it. So from our previous videos and whatnot, we know that we can start canceling things. So I have, well, let me write this out a little bit more. R squared is the same as saying R times R. And in the denominator, I have a 4 times a 1 over 3, which gives me 4 over 3. I have a pi, and then I have an R, R being a radius. So now let's start canceling things out. I have a 4 in the numerator and a denominator. Gone. My pi is gone. I have an R, I have an R, I have an R, I have an R. So I'm left with 1 R. And a 1 over 3. So I'm left with 1 over 3 times R. So R over 3, which will become there we have it. That is us simplifying an algebraic expression involving exponents. That's the end of the video. I'm kidding. This basically in math terms represents the ratio from between surface area and volume is 3 over the radius. We don't need to do anything with that. I was just using that as an example. What we are going to do is something much more fun now. Let's look at this. Let's say I have 2x to the negative 3 y squared This looks great. So let's start doing this one step at a time. So let's do the cube, the exponent out here first. So let's bring this in power of a power. So that's technically, you don't see it, but that's to the power of 1. So we have 2 to the power of 3. And then we have x to the power of negative 3 cubed. And then we have y squared, which is also cubed. And then in the denominator we have x cubed squared. And we also have y to the negative 4 squared. So if we were to write this out again, we're going to have 2 times 2 times 2 is 8. And then we have x to the power of negative 3 times 3, which is negative 9. And we have y to the power of 2 times 3, which is 6. And then denominator x to the 3 times 2. That is x6. division. So our 8 has nothing that is being divided by, but we have exponent x in the numerator denominator. So their exponents can actually subtract. And then we also have a y, which their exponents can also subtract, in which I am left with 8 x to the negative 9 minus 6, which is negative 15, and my y 6 minus negative 8, which is 6 plus 8, so 14, and my negative exponent. It's okay to write it like this, but if you want to get rid of the oh no. There. This big scary guy is now this guy. See, it's simple. So simple. Let's do another one. Let's try this expression. Say I have an expression, a very big one. Let's say x to the power of 2n minus 1 and 3, sorry, x to the power of 3 n, actually that's a plus sign, 3n minus 1 over x to the power of 2n minus 5. And now I want you to substitute x equals negative 3 and n equals 2. And now solve for this. What does this expression come up to? I don't know why I'm telling you this one, I have to do it. So let's do this. So our x is 3 to the power of 2 times 2 plus 1. Yep. And then, oh wait, negative 3, sorry. And then we also have negative 3 to the power of 3 times 2 minus 1 all over negative 3 to the power of 2 times 2 minus 5. So we're left with negative 3. 2 times 2 is 4 plus 1 is 5 times 3 times 2 minus 1 is 6 minus 1, it is 5 over negative 3. 2 times 2 is 4 minus 5 is negative 1. So now I can add the numerators, or I can actually evaluate this. 3 times 3 times 3 times 3 times 3. I don't know how many times I said it, but that's negative 243. Negative 243. And that's just over 1 over negative 3. So 1 over negative 3. If I punch this into my calculator, I should get 177, 147. And that is what that comes up to. And I know you might be thinking, when am I ever going to use this? I don't know, but I do know how to do it. Yay. So yeah, let's tackle this again. Except now, I'm going to, instead of plugging these numbers into this and solve them. I'm going to evaluate this. Like, simplify the equation first. So let's do that. So first, let's do the numerator, x. So if I'm multiplying these two exponents, I'm going to add those. 2n plus 1 plus 3n minus 1. So I'm left with x to the power of, so 2n plus 3n is 5n. 1 minus 1 is, okay, 0. So I have x to the 5n. And now the denominator, I have x to the 2n minus 5. So now I can divide the exponents, which means I'm going to subtract them. Which means I have x minus x 5n minus 2n is 3n minus negative 5, so plus 5. So now I can plug in these numbers. X equals negative 3, n equals 2. Negative 3 to the power of 3 times 2 plus 5, which is equal to 3 times 2 is 6 plus 5 is 11. Negative 3 to the power of 11 is also what a coincidence. So yeah, that was just to show you how simplifying the expression before solving can save you so much time. Let's do another scary one. So let's do 27 a to the negative 3. Let me write it again. A to the negative 3 times b to the power of 12 all to the power of 1 over 3 times 16a, divided by 16a to the power of negative 8 times b to the 12 to the power of half. So let's first bring in the power of a power. So 27 1 over 3. And then I have a negative 3 over 3. And then I have b 12 over 3. not uncommon for math class. Okay, now we're gonna have some fun. So, let's first rewrite this in terms of proper, like I want to clear up these square root signs. I'd rather just have fractional exponents. So I'm going to put x. So remember, root 5 of x is the same as x to the 1 over 5. So we already have an 8, so it's going to be 8 over 5 over x 3 over 2. And I still have my cube there. So the first thing I can do now is subtract these. 8 over 5 because I have a subtraction here. So 8 over 5 minus 3 over 2. Let's do the fraction math. I'll multiply that by 2, 16 over 10. Multiply that one by 5. Minus 15 over 10. So I'm left with 1 over 10. So x to the power of 1 over 10 cubed. And if I multiply that in, 3 over 10. And that is the same if I move it back into the square root. Boom. Well, just turn math upside down on us, and I hope I didn't cause too much pressure or pain. That has been I don't know what I'm doing here. Solving algebraic expressions involving exponents. And yeah, I hope that was helpful. And that's all for this long video, and I shall see you in the next one. Okay, in this video we're going to be looking at the exponential function and its transformation. So, a quick recap: the exponential function looks something like, well, it's something like that. So now we're going to be looking at transformations of this, like we did for our quadratic function and even the our linear one that we did a while back. So we're going to be looking at this function, y equals negative 2, 3 to the power of x minus 4. So right away, our parent function is going to be y equals 3 to the x. So if we were to draw that, at 0, at x equals 0, our y value would be 3 to the 0, which is just 1. And then at 1, 2, 3, 4, 5, 6, 7, 8. When x is equal to 1, 3 to the 1 is just itself. and then 3, 4, 5, 6, 7, 8, say 9. That would be somewhere here. And if you put 3 to the negative 1, you'd get like a very small number. So it'd be somewhere here. And it would just continue becoming a decimal number. And it would go all the way. It would just keep getting smaller. So here is our function. Y equals 3 to the x. So how are we going to make this y equals? Well, let me use a different color. Let's do now y equals 2. So whatever our y value was, now it's going to have a vertical stretch. So at 0, at x equals 0, we had 1, which was here, but now it's going to become 2. So our point will be here, and our 3 point will now go to 4, 6, and everything similarly like that. But also it'll still come back like that. But again, we have this negative sign, so actually let's do flip it on the x-axis, because whatever that value was now, it's going to be on the negative side. Oh, that way. That's very bad. But I try. Let's do now. We're going to do the movement on the x. So now we have an x movement. So this x minus 4 is in fact going to be a movement on the x-axis, but instead of, you might think it's going like when I have a negative 4, x minus 4, you think it would go that way, but in fact it's going that way 4 places. So here I am. And like, you could actually like plug this in like say you had y equals 3x and also 3x minus 4 when x is equal to 0. When x is equal to 0, our y value is going to be 1. When x is 0, our y value is 1. But now we're going to have a minus 4 instead. Well, it's not 3x, it's 3 to the power of x. 3 to the power of 0 is 1. But now this is going to be 3 to the power of negative 3, which is a very small number. So instead now, if I would have to plug in x to the power, I would have to plug in 4 for x to get 4 minus 4 equals 0 to get a value of 1. So this 0, 1. Now I have to have, 0, 1. Now I have 4, 1, which is all the way here. That is why this horizontal translation moves that way. And again, if you had +5 there, or +4, it would move the opposite way. So yeah, we have our reflection on the x-axis, we have our stretch, we have our horizontal movement. That's a lot of different moving pieces. So let's try one with one more addition. Say we have y equals 4 to the power of negative 2x minus 4 plus 3. So let's look at this. First, let's draw out our 4x. That's going to be somewhere 1, 2, 3, 4. So just approximate. Y equals 4x. But now I want to do, well, first let me rearrange this formula. That 2x, I can actually factor out the 2 and be left with x plus 2. So we have that. So one of the first things that I can see that I can do here, I have the x to the 4. Now I have the x values being multiplied by a negative 2. So when I have a negative in the exponent, now I have a reflection on the y-axis. And now that I have a 2 here, when you have a 2 here, that means you're going to have a compression of a factor of a half. So now our value is going to become, for one, it's going to flip onto, let me use a different color. So now this is going to be like that. So you can see that this one is closer to the line than that, because that is equal to y equals 4 to the negative 2x. So what else do we have? We have our, well, we're left with this, sorry. So now we're going to do our, I forgot that I factored out the negative 2, so 4 to the negative 2 times x plus 2 plus 3. And this one, we can look at this right here. Remember our x being shifted. That's going to be 2 units to the left. If we add 2 here, that means we're moving to the left. Previous example, we subtracted 4. We moved over to the right 4. So we're gonna go 2 units that way, and then we're going be honest with you, I didn't think I could pull that off. But yeah, step by step, logic by logic, and we will survive. So yeah, that has been exponential function transformations. Just scratching the surface here, but yeah, that's enough for one video. It should give you some idea of what I'm doing, and I shall see you in the next one. Okay, so in this video we're going to be applying the exponential function. So there's really only two types of problems that you're going to be using exponential functions. So that's going to be growth and decay. These are going to haunt you for many years to come if you choose to go into something math related and in chemistry. Just brought up a bunch of memories. So we're going to say that in the year 1996 we have a population of 35,000 in a city, right? And it has an annual growth rate of 8%. And now my question is, how long at this growth rate will it take for this population to double? So what we're going to do is use a formula, and our formula is going to be let's see. Okay, let's go with this. So, this is basically what you need to understand. This is a growth or even a decay formula. So, for the population to grow 8% from 35,000, if you were to multiply it by 1.08, that's basically giving it the 8% growth rate. You're saying that it's going to become 37,800. That's an 8% increase. And for it to go up again for 8%, you have to multiply it by 1.08 again, and you'll get 40,800. So now the question is, how many times it's going to take? How many times do I have to multiply this for this value to double to 70,000? Right? So, let's see. That's why in this formula we have n. That's the number of times we have to multiply this 0.18, which in fact means years in this problem, because we start in 1996 and then every year we multiply by 8%. How many years it's going to take if each year is 8%? So we're going to multiply it by 1.08 n number of times, and I need to figure out what that n number of times is. But I know that my population is going to be 70,000. if you were to continue doing it, then you would have basically 69,965 as a solution when you have n equals 9. So if you plug 9 in there, you end up with that. Or you could solve for n using algebra, and that would just be 2 equals 1.08 n. And then you could solve for this, but I don't think we've covered how we're going to solve for this yet. So I might cover that in the future. Let's see. Will I don't think we've covered it yet. Yeah, I don't think we've done this, but we'll take it one step at a time. But that's just an intro to this. So 9 years means by 2005 the population will double, just to give closure there. So now we're gonna look at a decay problem. We looked at growth, let's look at decay. So say we have, let me use a different one. 200 grams of some sort of material. Let's say it's plutonium or something. And the plutonium has a half-life of 138 days. What half-life means is that every 138 days, this will shrink by half. So after 138 days, this will become 100, then 50, then 25, and so on, every 138 days. So now we're gonna model this the exact same way. The mass that's left over based on our time that has passed by is our original amount, 200 times half, because that's what our exponent is going to be in the last one. We were growing by 1.08 here, we're decaying by 1.08. So 200 times 1 over 2 is 100, times 1 over 2 is 50. So how many times we're going to multiply this is going to be raised to the power of how many half-lives we're going to go through. So, but in this case, we're going to have this. So, one thing to understand is T is days. So, the question is, after 5 years, how much is going to be left over? So first what we need to do is say that, okay, in 5 years, 365 times 5, 1825. 1825 goes into our number of days. Why is that divided by 138? I'll tell you why. Because every 138 days, we're going to divide this. Sorry, every 138 days, we're going to multiply it into there. So, out of 1825 days, we're going to divide it by 138, and that'll give me how many times in this span of 5 years I'm going to have half-lives. How many times is this going to reduce by half? So, you plug that in, 1825 over 138. Then you're left with, if you punch this part into a calculator, you actually get like 0.000104, which means you're only left with 0.021 grams left. After 5 years, you started off with 200 grams And now you're only left with 21. So, another question here could be, oh, instead of finding out how much is left in 5 years, I could ask you, how long would it take for this 200 grams to become 110 grams? It's simple. Just plug in 110, 200. And solve. And now, again, I don't know if I showed you that part. But yeah, 0.55 equals 1 over 2. And then we can solve from here. But I would not. Well, we'll circle back to this method here. That is, in a future video, we're gonna have to go over logs and the logarithmic stuffs. But I think, as an intro to growth and decay, this is a good place to stop. But yeah, this has been applying exponential functions. Yeah, don't worry, we'll get into the stuff on how to solve for exponents on the other side. But until then, that's all for this one, and I shall see you in the next one. Okay, so in this video we're going to be doing trigonometric ratios of acute triangles. So if you remember, acute are angles that are less than 90 degrees. So when we are dealing with angles that are less than 90 degrees, that means we have one angle that is 90 degrees in the triangle. Well, not necessarily, but what we're going to be doing in terms of trig ratios, just to recap. SOHCAHTOA, sine, opposite, hypotenuse, cos, tan, and A is adjacent, and hypotenuse, and O is opposite. So we have our SOH, sine theta is equal to opposite over hypotenuse. Cos theta is adjacent over hypotenuse. Tan theta is opposite over adjacent. So now that we have our trig ratios, we can look at an example like that one. Say we have an angle of 16.7 degrees. And I want to find out, let's say I have a 3-meter height here. I want to find out this guy right here. Let's call this x. So, let's say I want to find that out. So I'm going to be using my tan ratio because I have an angle and then I have the opposite and I'm looking for the adjacent. So I can do tan theta equals O over A, which tan theta is equal. This will now be written as tan of 16.7 degrees is equal to opposite, which is 3 over x. So now if we were to rearrange this, we can put this as x equals over tan 16.7 degrees. And if we were to punch this into the calculator, say we do that, I have tan of 16.7 is 0.3, and if I do 3 over that, I get 9.9999, which is about 10. So our x is equal to 10. So if you have something that is 10 meters long and 3 meters high, or 10 meters away and 3 meters high, the tip of that to here is going to be 16.7 degrees. And yeah, like, this video is kind of more of a recap of things that we have done in the past. So let's say we have another problem where we have this triangle 28, and this is a right angle. So say I want to find out this length here, and again, as a recap of what we used to do in the past, this is basically one of those A, B, C, where A squared plus B squared equals C squared. So I can actually write that out. 8 squared plus 20 squared equals C squared. C being this long side. So if you were to write that out, you would get 20 squared is 400, 8 squared is 64, so 464, and C is equal to the square root of that. So I would end up with about 21.5. And now we have 3 different angles here. Sorry, that one's 90. But we have these two, theta 1 and theta 2. And I could actually start solving for these. Say I wanted to solve for this one, theta 2. I know that the tan of theta 2 is opposite over opposite, which is 8 over 20. So I can put that in. 8 over 20 is about 0.4. So tan of theta 2 is 0.4. And if I was to punch that into the calculator, I could do inverse tan of 0.4. I get about 21.8. I can round that too. That's how I write, or you write, everybody writes inverse tan. And now I have 21.8. Now, I could actually use another trig ratio to find this one. I could do the tan of this one and make that the opposite, and that's the adjacent. Or I could do a cos, where this is the adjacent and that's the hypotenuse, or opposite and hypotenuse. I could use each one of them. Or I can do the rule where the angles inside the triangle all add up to 180 degrees. So 90 plus 21.8 plus I have theta 2, I'm looking for theta 1 is equal to 180, so theta 1 is equal to 180 minus 90 minus 21.8, 68.2 degrees. And I don't know if we have gone over reciprocal functions, but let's introduce them here. I doubt we have. But basically, when we have something like sine theta, there is a reciprocal function of this, which is cosine. The word is literally slipping my mind right now. CSC. I believe it's cosec. No, yeah. I'll have to come back to that. And for our cos theta, our inverse is sec theta, and for our tan theta, our inverse is cot theta. And CSC is the same as, or is equal to 1 over sine theta. That's what the reciprocal is. As our sec theta is 1 over cos, and our cot theta, cotan, is 1 over tan theta. So while you might remember sine theta is opposite over hypotenuse, CSC theta is the reciprocal. So our hypotenuse over our opposite, while cos theta was our adjacent over our hypotenuse, the reciprocal is now our hypotenuse over our adjacent. And while our tan theta was opposite over adjacent, our cotan theta is now adjacent over our opposite. So these are our 6 trig identity or functions, our ratios, our sine theta, our sine, our sine, cosine, and tan theta. And then we had our reciprocal functions here. 1 over sine, CSC theta, sec theta, and cotan theta. So, I hope you remember these because we're going to be using them in the future in much more confusing ways. So for now, that's all for this introductory video to these trig ratios, and I shall see you in the next one. Okay, so in this video, we're going to be looking at special angles. So special angles, as we'll learn, are going to be triangles with 45-degree angles or 30 and 60-degree angles. So, say we have this, where this is 45, this is 45, and this is 90, right? If you were to just flip that, you'd get a square. And then we have the other one where we have 30 and 60. this, you would get a triangle. So we can actually calculate the sine, cosine, and tangent for this one on a 45-degree angle. So if we were to have these angles being the same, that would mean that this length and that length are going to be the same, because if they varied, then we would have different angles. So say we have this side is equal to 1, and this side is equal to 1, right? If I want to find out the hypotenuse, I could use the Pythagoras theorem to find that out, which is 1 squared plus 1 squared equals, let's call it h squared. 1 plus 1 is 2. So the hypotenuse is the square root of 2. There you go. And now let's look at, because I know these are 45-degree angles, and it doesn't matter which angle I look at, cosine or tangent, from whichever angle, I'm going to get the same ratios because they're the same from whichever angle you look at. So let's look at an angle through our trig ratios, which is, let's do sine first. Sine 45 is equal to opposite 1 over hypotenuse. And then our cos 45 is equal to adjacent over hypotenuse, which is the same, 1 over. And then our tan 45 is equal to opposite over adjacent, 1 over 1, which is 1. So there we go. One thing to note, this root 1 over root 2 is the same as root 2 over 2. It's just easier number to use when doing calculations. If you continue to pursue math or a field in math, you're going to actually memorize all the sine, cosine, and tan values by heart for 45, 30, and 60 degrees, and 0 and 1. But I can actually show you an easier way to remember that. So let's look at this. Our 60 and 30. So say we have 60 and 30. Let's put this as 1. Let's put this as 2. And let's call it 30, and that's 60. Now, one second. So if we have 2 as our hypotenuse and 1 as our one of our edge values, then through Pythagoras theorem, we can do 2 squared is equal to 1 squared plus, let's call this x squared. So 2 squared is 4 minus, I'm going to bring this over 1. So the square root of 3 is x. So I'm just going to write that there, root 3. So now let's start writing the trig ratios for 60 degrees. So for sine, let's do 60. Sine 60 is opposite root 3 over the hypotenuse 2. Cos 60 is equal to adjacent 1 over hypotenuse 2. Tan 60 is equal to opposite over adjacent, which is root 3 over 1, which is just root 3. Similarly, I can write them out for sine. So, if I was to do them for sine, then sine opposite over hypotenuse 1 over 2. I have cos of 30, which is adjacent over hypotenuse root 3 over 2. And then I have 1 over, tan opposite over adjacent 1 over root 3. And again, root 3 over 3 can also be written as 1 over root 3 can also be written as root 3 over 3, just to make it easier in calculations. When can you actually use these identities, these special values? Say we have a problem where we want to do sine 45 times cos 45 plus sine 30 times sine 60. So I know that from my special angles. Let me just put it in for reference. Sine 45 is root 2 over 2, which is so I can write that out. We'll see what my cos 45 is also root 2 over 2. And then I can do my sine 30 and sine 60. So sine 30 is 1 over 2. And my sine 60 is root 3 over 2. So now that I have my values for my special angles, I can just do my fraction math. Root 2 times root 2 should give me 2. The denominators will multiply. Root 3 over 4. And now I'm left with let me write it here. 2 plus root 3 over 4. And you can actually punch all this into a calculator and punch this into a calculator. They'll become the exact same value. So, one thing I can actually show you that one of my favorite teachers showed me in school is the sine, cos, and tan values of 0 degrees, 30, 45, 60, and 90. I can make a chart from this very quickly. And that is by doing this. I can do 0, 1, 2, 3, 4. I just write down 0, 1, 2, 3, 4. Put them, square root that all. And then put them over 2. And now let's just evaluate these quickly. 0 over root 2 is 0. Root 1 over 2 is 1 over 2, because the root of 1 is 1, so 1 over 2. that's my first row. The second row, I'm going to write this backwards. So I'm going to write 1. I'm going to write this 3 over 2. I'm going to write, well, this one doesn't change in order. And I'm going to put 1 over 2. I'm going to put that 0 here. Now, I'm going to take this value and divide it by that value. 0 over 1 is 0. 1 over 2 divided by root 3 over 2. 1 over 2 divided by root 3 over 2, which is flipping and multiplying, so 2 over root 3. These cancel, so I'm left with 1 over root 3. And then I have root 2 over 2 divided by root 2 over 2. These two values are the same, so that's just going to be 1. And then this one, let me write it somewhere here. Root 3 over 2 divided by half, so multiplied by 2. These cancel, I'm left with root 3. 1 over 0 is undefined because you can't divide by 0. So now I have this chart of 15 values. I'm going to write sine here, cosine here, tan here, and then I can write 0, 30, 45, 60, and 90. And there you go. I used to do this in the beginning of trick tests just so I have all these special identities. These are my degrees. Sine of 30 is half, cos of 60 is half, tan of 45 is 1. It was a very quick way to just, instead of just memorizing everything, I was able to just chart this out really quickly by doing these 0, 1, 2, 3, 4, square root all of them, divide them all by 2, writing them out, reversing the order, dividing it to get the tan, and boom. That is how I cheated my way through math. But yeah, those are special angles. I didn't show 0 or 90 in this one, but in future videos when we're dealing with circles, you may actually see them, so stay tuned for that. But for now, that's all for this video, and I shall see you in the next one. Okay, so in this video, we're going to be looking at trig ratios for angles between 0 to 360 degrees. So up until now, we've been really looking at acute angles, so less than 90 degrees. Now we're going to be looking at angles bigger than 90 degrees. So the main difference is that all the triangle angles we've been looking for, if this is 90 degrees, this is 180 degrees, this is 270 degrees, technically this is 0 and also kind of like 360. But yeah, that would be a full circle. Basically, when we have an angle, or in our videos, our past couple videos, when we've been doing trig ratios, we've been looking angles really over here in quadrant 1, and this is quadrant 2, quadrant 3, quadrant 4. Here we have 0 to 90 degrees. Here we have 90 to 180. Here we have 180 to 270. Here we have 270 to 360. So this is going to be very important for us. Up until now, we've been doing our sine, cos, and tan ratios in quadrant 1 with 0 to 90 degrees. But now we're going to be looking at problems that are going to go into quadrant 2, 3, and 4. And one thing to remember is this. No, wait, I messed this up. It should be CAST. That is correct. Ignore this. So, remember this cast. All this basically means is, in quadrant 1, when we have A, that means sine, cos, and tan. When we do any of these operations on the angle, we're going to have a positive output. So it's going to be a positive number when we do the inverse sine or inverse cos or inverse tan. In quadrant 2 we have an S, so here only sine will be positive. The other two will be negative in this quadrant. Similarly, in quadrant 3, only tan will be positive. Sine and cos will be negative in quadrant 3. And in quadrant 4, we have cos, that'll be positive. And sine and tan will be negative in this quadrant. So these are just some things to remember as we start looking into these things. Let's start with maybe an example. We can do quadrant 1. Let's say we have a point on a graph 3, 4. That is my line. So I know from this triangle and this theta, this is basically the triangle. I'm going to make 3, 4, and I know from Pythagoras theorem 3 squared plus 4 squared is 25. Square root of that is 5. And then I have an angle. So now I can find this angle to the nearest degree. Let's just, we can do any sine, cos, or tan. If I write out the trig ratios, sine theta is opposite over hypotenuse, which is 4 over 5. Cos theta is equal to adjacent over hypotenuse. Tan is opposite over adjacent, which is 4 over 3. You can punch any one of these into the calculator, and your theta will give you 53 degrees. And notice how these are all positive ratios, because we are in quadrant 1. But let's say, instead of in this quadrant, I want to choose it in this quadrant over here. I choose to do -3. And the same y value. Now I want to find out this angle. Now, let's try doing the exact same thing. Well, for one, our Pythagoras theorem will give us this to be the same because we're squaring it. Doesn't matter if it's -3 squared plus 4 squared. This is still going to be positive, so that's 9 plus 16. Right? So, if we were to write these trig ratios out again, now we have this 4, 5, but -3 here. It's in the negative, on the negative x-axis. And I'm looking for this angle, so if I was to write these again, sine is equal to opposite 4 over 5. Cos theta is equal to adjacent -3 over hypotenuse 5. Tan theta is equal to opposite over adjacent over -3, so that's a negative. Now you see why, from our cast system, S in quadrant 2 is the only one that is positive. The other two are negative ratios because they're in this quadrant. And you'll see that once we go into tan, if we do the same, Well, again, if you were to do these inverse of these, you should get the same. Theta equals 53 degrees. Let's do another one. Now let's go into the next quadrant. If we were to go into quadrant 3, like down here, -4, -3, let's go like this, -4, -3. This is still going to be a positive hypotenuse. So now, if you were to write for these angles, if you were to write these out, you would get sine opposite over hypotenuse, -4/5. Cos theta is equal to adjacent over hypotenuse. Surprisingly, tan opposite over adjacent, -4/-3. The negatives will cancel out and you're left with 4/3. And that's why your tan is positive in quadrant 3. And now let's do the last one. -3, no, this is +3 and -4. That's the point. Angle, we still have 5. If you were to write these out, sine theta is equal to opposite, -4/+3. Sorry, hypotenuse 5. Cos theta is equal to adjacent 3/5. Tan theta is equal to opposite over adjacent, -4/3. And again, you'll see cos is positive in quadrant 4, tan is positive in quadrant 3. And that's basically what it is. So, another thing that I didn't do though is explain to you the angles when it's in different quadrants. So, if you were to solve for all these thetas, you would get 53 degrees. But 53 degrees only makes sense in this one. Like this right here. But over here, we have to take the angle starting from this line here. So from here to here is what? If this angle is the same as that angle, then we have to do 180, which is this line here, a full 180, minus theta, which is the one that we found. 180 minus 53 is 127 degrees in there. And then similarly, we have to do the same for quadrant 3, which is here. And that is from here all the way like that. So now we have 180 plus 53. And that will give us 233. And then we have our final quadrant, which is going to be here. And this is much easier. We just do from here all the way around. A full circle would be 360. We're going to do 53 less than 360. And we're left with 307 degrees. So there you have it. We have 53 degrees, 127, 233, 307. That is how the CAS system works. And this is going to come in handy for us when we we start using logic to come up with where the angle is. So if I was to tell you that, for example, CSC theta is equal to negative 2 root 3 over 3, and I was asking you where is this? So by logic, you can just do, this is 1 over sine, so just take the reciprocal of that. So sine theta is equal to negative 3 over 2 root 3. And if you have a negative sign, that means it cannot be in quadrant 1 because everything is positive in quadrant 1. It cannot be in quadrant 2 because sine is positive there. It has to be either in 2 or 3. And that's where, and in quadrant 2 and 3, that's where theta is, the angle. When we solve for theta equals, if you put the inverse of this into a calculator, you should get, let me try punching this in. 2 times root 3 over answer times negative 1 inverse sine. Oh, I get negative 60. So yeah, I get a negative 60. So that means my negative sign in my negative sign ratio, which we have said is going to be in quadrant 2 or 3, I have 180 plus 60 or 360 minus 60. So now I have either 240 or 300. These are my two solutions. And that's how we're going to be solving trig ratios moving forward using the gas system here, because this is going to be very important to understand, and understand why certain things are positive or negative in each quadrant because of how the ratios apply. So that's all for this video. It's just an intro to the gas system, and I shall see you in the next one. Okay, so in this video we're going to start looking at trig identities, and trig identities are going to help us when we start doing solving trigonometric equations and simplifying them. So right off the bat, let's do the ones we already know. We had our sine, cosine, and tan. We had these three already. So we remember our reciprocal functions. Those are going to be our first ones. Our CSC is 1 over sine theta. Our sec theta is 1 over cos theta. Our cot theta is 1 over tan theta. These are the ones we already knew from our previous videos thus far. So one of the identities that we're going to look at is this one. And this is always, well, this is just a true fact in terms of what it is. So why we can actually prove this if we have a triangle, right? Theta, and let's call it x, y, and z. And if we were to write this out, we have sine theta is equal to y over x. Y, opposite over hypotenuse. Y over z cos theta is x over z, and we have tan theta is equal to opposite over adjacent, so y over x. So if we were to divide these two, sine theta over cos theta, which is, if I was to plug these numbers in, or variables in, ratios divided by this will become a flip, we'll cross multiply, but basically y over z times z over x. The z will cancel and you're left with y over x, which is therefore, well, I'll just write therefore this identity is true. So now we can do another one. If we were to do the exact same logic as this, there's another identity. So we know that sine squared theta, which is just like saying sine theta times sine theta. We don't write sine theta squared, we write sine squared theta. So we can put that in y over z squared plus x over z squared. And if you were to actually open up these brackets, like do the order of operation of y squared over z squared plus x squared over z squared. So now you have x squared plus y squared over z squared, right? And if you look at this right triangle right here, the one that we were referencing the entire time, x and y are the two sides that we use to find out the hypotenuse using Pythagoras theorem. So in this case of the Pythagoras theorem, I'll write it here, x squared plus y squared equals z squared. So using this logic, x squared plus y squared is equal to z squared. I can rewrite this numerator as z squared, and I still have z squared in the denominator, so that's 1. That's why this is equal to 1, and this identity holds true. Let's look at another one. We have another one. Let's do 1 plus so let's start looking at this. How can we prove that this identity holds true? Basically, I'm going to do it in 2 steps. One, I'm going to do this side. C as c squared theta is the same as 1 over sine squared theta, which is the same as 1 over sine theta squared. Remember this is my, let's call it my right side. Now my left side, 1 plus cot theta. Remember, cotan is 1 over tan. So similarly here, 1 plus steps here. But basically, remember, tan theta is equal to sine theta over cos theta. So 1 over tan is going to give me the reciprocal cos theta over sine theta squared. That's still here. So cot theta is equal to that because sine theta is equal to sine over cos. So cot theta will be equal to the reciprocal cos over sine. And remember, we still have the squared sign here. So that's all I did. And now the next step, I'm going to put the square in. 1 plus cos squared theta over sine squared theta. That's all I did. I brought that in. But now, if we were to add this, like this 1 plus that, if I was to make a common denominator, I can do sine squared theta over sine squared theta plus cos squared theta over sine squared theta. So, what do we have here? All I did was take this 1 and turn it into a sine squared theta over sine squared theta, which is still equal to 1. And now now that I have the common denominator, I can just add these two. I have sine squared theta plus cos squared theta all over sine squared theta. And if we remember our identity, sine squared theta plus cos squared theta equals 1 from our Pythagoras theorem, that means the numerator is now 1 over sine squared theta, which is also 1 over sine theta squared. That is equal to that. Or even this is equal to that. Or even this itself, I could rewrite it as CSC squared theta. And that proves this identity right here. So, what else can we do with all this stuff? All this good knowledge. Maybe we can do one more. We can do one more. Say, on a test or something, you get this. Say, they give you this and say, prove it, that tan theta is actually equal to all this. So, tan theta, I'll leave it as is. The only thing I can speculate about that is tan theta is equal to sine theta over cos theta. That's all I have. I'll leave that on that side. On the other side, what can I do? First, I have sine theta in both terms in the numerator, so I can factor that out. So I have 1 plus sine theta. Now my denominator is still the same. And look at that. I have in the numerator and denominator 1 plus sine theta. I can cancel that out. And boom, I'm left with sine theta over cos theta, which is also equal to tan theta. And that's how simple it is. You don't have to let any of this intimidate you. Just remember your identities. Remember who you are. Wise words of Mufasa. Okay, so that's all for terms of this video, that's it. And I shall see you in the next one. Okay, so in this video, we're going to be looking at the sine law, more of a refresher. Sine A over A is equal to sine B over B, or even inversely. Where the lowercase a and b represent the length of a side, and the uppercase represents the angle. So say we have a problem like such, where we have C, A, and B, where B is 7.8 meters, A is 5.9 meters, and this angle is 36 degrees. And now I want to find out the angle of B. So let's start plugging in some numbers. Remember, this is a refresher, so you should know how to do this by now. If not, you can go back into previous or old videos, and I have it explained in those ones. So let's do 5.9, and over its opposite angle, sine 36 degrees is equal to 7.8 over sine B. So with a little bit of rearranging, I'm going to bring the sine B up to that side. Multiply this sine 36 up that way, and bring that 5.9 down here. And I'm left with this. Yeah. So my B is equal to the inverse sine of 7.8 times sine 36 over 5.9. And if I punch that into a calculator, I should get 51 degrees. And now, with my triangle law, I know that 36 plus 51 plus C will give me 180. So I can subtract 36 and 51 from 180 to get 93 degrees for C. And there you have it. And now, with that angle, I could just simply punch in the same 5.9 sine 36 is equal to sine 93 that I got. That's that one over C. So now C is going to be 5.9 sine 93 over sine 36. Punch that into a calculator, and I got about 10 meters. Remember, I have meters in my units always. So yeah, math is really definitely fun. So let's look at another example of another triangle. Let's do one with a bigger angle. Let's say this angle is 140, and I have this 15.6 meters here and 36 meters here. So let's say that this is an imaginary x-axis. And I want to find out the angle here. How am I going to do so? And let's say this line here is going to be parallel to the ground. I forget how to spell. Anyways, so let's try to find this angle. And from our angle laws, we know that when you have a C shape, this angle is the same as that angle. So actually, I want to find this angle. And now it just comes back down to a silly sine law equation. So if we start punching these numbers again, we have this sine theta is equal to sine theta over its opposite length, 15.6, is equal to sine 140 over my 36. So if I multiply both sides by the 15.6, this will cancel out and I'm left with sine theta equals 15.6 times sine 140 over 36. And yeah, if I start punching this into the calculator and take its inverse theta, then I should get about 16 degrees, or 16.1 or 2. But basically, once I found this angle, I can say that that is equal to this angle. And there you go. That is a quick refresher of the sine law. I think next we're going to be looking at the cosine law. Just as a refresher for, actually, you know what? Why split it into two videos? Let's just dive into it. And if you remember the cosine law, yeah, it should have been, if I'm looking for, let me do this in a different light of color. Let's do this one. I have a squared equals b squared plus, I need more space. And as well as yeah, that should basically be it, because if I have any triangle, so if I have these two that I'm looking for, well, basically cosine law, if I have the three sides and I'm looking for one angle, or any angle, I'm looking for an angle, I can use this. If I have A, B, and C, similarly, if I have, say, A and is not going to be here. A is going to be on that side. If I have C and B and the angle in between, I can punch this in. It's very, those are the two times that I can use the cosine law to find things. So let's actually try this out. Just a quick example. Let's do 55, 32, and 26. And now I want to find, let's say I want to find this angle. Let's call it cos A, because that's what I'm going to be plugging in here. That'll be my A. So let's do, let's punch these in. So 55 squared. Let me write it here. 55 squared is equal to 26 squared plus 32 squared minus 2 times 26 times 32 times cos of A, which I don't know yet. So I can start bringing these over and subtracting them. So that'll give me 55 squared minus 26 squared minus 32 squared. And on this side, if I'm left with this term only, I want to get rid of all that and just isolate the cos A. That's all being multiplied by all this, so I can divide it. So now I'm left with this, and all I really have to do now is take the inverse cos of that, and I'll get the angle A. So if I punch all this into a calculator and get a number and do the inverse cos of that number, I should get an angle of about 143 degrees. And that is a example of us using the cosine law when we have three sides and we want an angle. But if we have, say, another example, say like this. Say I have 10.6, 22.9, and I want to find out the side B. And I have this angle 26. I have the angle and the two sides to it. Let's pretend this is straight. Okay, now I can use the cosine law again, where in this case, this will be technically my A, because I have the opposing angle. So technically this is going to be, I can even call this A, just so I don't confuse anybody. So I'm going to have A squared is equal to the two sides, B and C, 10.6 squared plus 22.9 squared minus 2 times 10.6 times 22.9 times cos of 26 degrees. Oh no. Let me write it back here. A squared equals 10.6 squared plus 22.9 squared minus 2 times 10.6 times 22.9 we use both the cosine and sine laws. So look at it like this. Say I have this triangle, and I have angle A 60 degrees, but B, so that's capital B. I have this theta here, and I have C, which is also equal to 5.1, and this is equal to 8 meters. Now, say I wanted to solve for this angle. So right now, I cannot use the sine law because sine law requires me to have at least one angle and its opposite length to be able to do the other calculation. So I have this and that. So I could do sine theta over 5.1, but I don't have anything to compare to. I don't have 60 and B, I don't have A and 8. So I can solve for one of them. And let's try solving for B in this case. So I'm going to solve for B because remember my cosine law where I have the angle and the two sides. I can find out the opposite length. So I have this angle and measurements for the two sides. So let's punch that in. I got B squared is equal, because that's B. And I have the other two, A squared plus C squared minus 2 AC cos B. So if I was to plug this in, I would get B squared is equal to 5.1 squared plus 8 squared minus 2 times 5.1 times 8 times cos 60. Sorry. And if I was to solve for this, I should get about 49.21, and B will be equal to the square root of 49.21, which is about 7 point something small. But I'll use 7 for now. So that's equal to 7. Now I have my sine 60 over 7. Now I can use the sine law and just solve for that. So my sine theta is equal to 5.1 sine 60 over 7. And my theta is equal to the inverse sine 5.1 times sine 60 over 7. Punch this into a calculator and you will get theta is equal to 39 degrees. And there you have it. And you could even add this to 60. 180 minus 99 should give you 81 degrees. That's going to be this. Using the logic that the angles will add up to 180. So yeah, that has been the cosine law and everything, the sine law. Just a refresher. So I hope that was a good refresher, and we'll see you back here in the next video to do something more confusing. And that's all for this one. So, see you in the next one. Okay, so in this video we're going to be tackling 3D problems, 3-dimensional problems involving trigonometry. So let's say we have a cliff say this is the cliff and this is the height up. Call it H, and I'll call this point A. And then I have this point here. I'm gonna call it B. And I'll call this point C. And let's say that this is a right angle. It's going up. Elevation, this is the ground. This is the top of the cliff. And let's say I have another point here on the ground. Point D. And the angle here is going to be 42 degrees. And the angle, the length here is 68.5 meters. And I have an angle here of 63 degrees. And I have an elevation angle up here from the ground up of 38 degrees. This here is a right angle, but this one is not. This angle here is not a right angle. I'm just not good at drawing. So, let's start solving for H. Okay? So one of the first things I can do, I have two angles here very quickly. I can solve for this angle here. So 180 minus 42 minus 63 is equal to 75 degrees. And now I have that. So once I have that, I can actually look at, because I have this angle and its opposite length, I can use the sine law. Oh, let me do the other way around because I want this right here. I want that one right there. So let's do 68.5 in the numerator and sine 75 in the denominator. And now I want this length here. I'll call that x. So I have x over sine 42, which is there. So now I'm able to use the sine law to solve for this line here, or that distance. So that'll give me x equals to sine 42 over sine 75 times 68.5. And if I put this into a calculator, I should get 47.45 meters. So that's 47.45. So now here I am again. I can use the sine law again. I have this with this angle here, which I can calculate very easily because I know that that's a right angle triangle. So I know that actually, hold on, I don't need to use the sine law if this is a right angle triangle. If I was to redraw this, that's 47.45, and that's an angle of 38, and I want to find that. I can just use my 10. Opposite over adjacent. So my H is going to be 47.45 times tan 38 degrees. Well, that worked out. So I'll just plug that into a calculator and get 37.1 meters. Well, that was a lot easier than it looked like it was going to be. Maybe we can do another one. Let me draw another problem for us. to say that is 1. And then I have another one over here, which is also a right angle. And then I have this right here. So, this is going to get very confusing very quickly. But I'm going to try my best not to confuse anybody. Let's try creating a grid here. Let's just say, let me use a different marker. What I'm about to draw is basically a Cartesian plane where this points north. And then this will go like that. Let's pretend that's a straight line. So a couple things to note here is that from this line here, this red line, this angle is going to be 120 degrees. And then we have this line here, from here to go all the way around. That's going to be 230 degrees. And now I want to find the distance between A and B. Another thing that I'm given is this length here is 50. So, based on what we have, let's start going to work on this. So, the reason why we have these two measurements, very quickly I can redraw this and find this angle right here. Because if the whole thing is 230 and only up until there's 120, I can just subtract the two and get 110 degrees. So if I was to redraw that, that's 110. That's 50. Is this one right here. And now I can also look at what else can I take away from here. If I have 180, if this is a right angle and this is a right angle, let's see. What else can I take away from here? Okay, if I was to look at here, 230 degrees to 120, then I could assume that if I was to look at it from a bird's eye view, if that's 230, then and the 3/4 way is 270, then I'm 40 degrees off here, 40 degrees off there. Okay, again, that doesn't do much for me. Oh, I understand what went wrong here. I forgot to give us some guys. So let's draw that bigger. Let's call this length here A. Let's call that one B. Let's say this is 50. This angle is 38. This angle is 35. I'm looking for this. So yeah. Let's start doing some problems. I remember 110 degrees. Let us start looking at how we can approach this problem. So, oh yeah, remember this is, these two are right angle triangles. So let's look at these ones individually. So we have on this side 50, a right angle triangle, and then an angle of 38. That is here. So if I wanted to find this B right here, I can just use tan 38 is equal to 50 over B, which is B is equal to 50 over tan 38. Similarly for this one, B is going to be equal to 64. So I can write that 64 approximately. And then same with this triangle here. That's 50. This one was 35. That's A. So I'm going to have tan 35 equals 50 over A, and A is equal to 50 over tan 35, which will give me A is equal to 71.4. So let's put that in here. 71.4. So, lo and behold, I have two lengths and an angle in between. And that means I can use my world famous cosine law. So let's start punching these numbers in. So let's do, I have x here. Let's do x squared is equal to 64 squared plus 71.4 squared minus 2 times 64 times 71.4 times cos of the opposite angle. And from here on out, it's just smooth sailing. It's all just calculator work. X is equal to about 111 meters. Wow, that was a lot of, it almost confused me, because I missed these points, these angles of depressions from the problem. I completely oversaw them, forgot about them, but yeah, very simple steps. Finding this angle in the middle here, the 110, was just because they gave me these two angles here. 120 to here, 230 to there, subtract those, and I get this angle in between. I have that, these angles of depression, if I use that C logic, Oops, I'm going to stay away from them, but that's all for this confusing video. I shall see you in the next confusing video. Okay, so in this video we're going to be looking at periodic functions. So a periodic function is some sort of function that indefinitely just repeats itself again and again and again. So it might just look like wavy lines, but this is actually a function that is repeating itself. So let's say from here, or let's look at this right here to here. This part is the same as this part right here. Let's say it drew it exactly the same and not all messed up. So when you have a function like this that keeps on repeating itself, this is a periodic function, and there's so many different types of them that we can look at, and we're going to look at. But first, let's look at some of the properties. So first, a periodic function. What is that? By definition, textbook is a function whose graph repeats itself on a regular interval. The y values will show you a repetitive pattern when the x values change by the same amount, meaning the height here, or the y values, will be the same repetition after a certain amount of x. So by definition, we're just repeating ourselves again and again and again and again. So one thing we need to define or learn is what is the period when we are talking about a function. So a period can also be remembered by the word cycle. So from here to here we saw that's one period. That is one cycle, and then that is another one. So these are each one period each. So if you're ever asked what is the period of this, and this goes, say this is x equals 1, and this is x equals 5, you know that the next one ends at, the difference is 4, then the next one should be 9. The period will be the same as it repeats itself. So let's look at another thing. There's another word we have to remember. Draw. And basically, well, this goes hand in hand with peak. So peak is self-explanatory. It's the peak, the highest point. Draw is the exact opposite. The lowest point. What else do we have? Let's do something called the equation of the axis. So the equation of the axis in this case is the x-axis. Basically it's asking, one quick way to find out is take the peak, add it to the draw, and divide it by 2. And there you have the the equation of an axis. So that in this case it'll be x equals 0. Because I drew it centering it on the x-axis. Sometimes you might have a little up or a little bit lower. that you have to do or remember is amplitude. So the amplitude is the distance from the equation of an axis to its maximum point or minimum point. So we drew a line through this, and let's say the peak is at 10 and the draw is at -10. Our axis is 0, so our amplitude is going to be this. It should be 10 on both sides. So I guess this was a pretty much a very simple introduction to periodic functions. I guess it's going to be shorter than the other videos that we usually do. In the future, or the next upcoming videos, we're going to actually take some examples and look at the sinusoidal wave, or well, there's something called the sine. Well, when we did our trigonometry section, we learned about sine, cos, and tan, and they each have their own wave, and also their inverse functions, which are actually, if you write it out, it's the CSC wave. CSC cosine, I forget what the other one is called. We have a cotan wave. And we had one more, our cosine. Oh, the name eludes me right now. I'll remember it when I remember it. Oh, sorry. Our sec function. Yes. So we're going to have all these waves that we're going to draw out and we're going to play with. And we'll actually even plug them into like real world scenarios on when we use these waves. Particularly if you go into physics or any physics related areas, you're going to be seeing a lot of wave functions, so that is going to be really fun. But yeah, I think that should be enough for this video. I will see you in the next one. Okay, so in this video we're going to be looking at sinusoidal functions and how we can transform them. So, in previous videos, we have looked at how we could transform a quadratic function, and we did have that formula. I believe it was a x minus, what was it? I think it was a times kx minus, I forget what it was. I'll just write d for now, plus c, where a was the vertical compression or stretch, k was the horizontal one, d was the horizontal shift in the x direction, so this way or that way, and c was the vertical, up or down. So when it comes to sinusoidal functions, and we have, say, the two graphs, we have our main ones. Let's start with the basics. Y equals sine x and y equals cos x. So let's actually draw this one out. The y equals sine x. So we have let's say this is 0, and that is our y, this is our x-axis. Let's say this is 1, and this is -1 on our y. When we have y equals sine x, this is basically going to go in increments, or a full period is going to be 180 degrees. So our x-axis is actually going to be written in 180. Oh, sorry. My mistake. It's actually a full revolution, because I have to look at it in the form of a circle. So imagine this angle here, when it goes, if this was to go all around like a clock, counterclockwise, when you were to graph this out, you would start here and then make your way that way and come back around. So if you were to move this, you would basically have something like this, where you start here, and as you're moving in that direction, and you're going counterclockwise, so from 0 to 360, and this is 180, so you're going to go, and then this is, say, 90. From 0 to 90, you go up to the max, and then from 90 to 180, you come back down to where you were, and then from 180 to 270, you go to the lowest point, and then you come back to the main point. So let's draw that out. 360 degrees. Let's say that's 180, and that's into 4 points. So let's just pretend that's symmetrical. And there you have it. That is our sine graph. And our cos graph is very similar, actually. But our cos graph does not start at 0, because cos of at 0 is going to be actually 1. So we'll still have our 360. But so these are increments of 90. So this one we're going to go from cos, and then at 90 we're at 0, and then at -1 we're going to be here, and then we're back to 1. It's 360. Supposed to work. Yeah. So if you were to draw these together, it could be something like this. So this is cos x, and this is sine x. So we're going to bring this in, this formula, and we're going to apply it here, because when we think about transformation of these functions, it's the same as these ones, are very close actually. So we're going to have f of x is equal to a sine k x minus t plus c. And then for our cos, which is the same, we're going to have f of x equals a cos k x minus d plus c. So let's actually look at one example. Let's write that formula out first. F of x is equal to a sine k x minus d plus c. And now I'm going to write out our example. F of x is equal to 3 sine 2x minus 60 degrees plus 4. So let's start off with our y. So let's do x. And we're only going to draw one period here. So let's say this is 360. I'm going to say this is 1, 2, 3, 4. 1, 2, 3, 4. And you may see why. So remember, well, that might be a little long, so let's do, say 360 is somewhere here, and that's say this is 90, 180, that's 90, 270. As we know, the sign goes from 0 to 90 through 180, and then it comes up to here, and then repeats itself, but we're not going to ignore that. So I'm going to say that this color is y equals, or f of x is equal to sine x. And now let's go with a different color with our first transformation. So let's do the let's do this one now. F of x equal to sine 2x. And what that basically is a horizontal compression. If we have 2 here, that means we're compressing it in half. So now, instead of doing the full period into 360, we're going to do it into 180. So now, wherever it crossed at 180, it will now cross at 90. So now, instead of at 90 it peaks, it's going to peak at 45. And that's it. That is our horizontal compression by 2. And then we can actually move it over. Let me use a different color. this. It's the opposite sign for it. So now wherever these points are, we're going to move it 60 over. So now instead of at 90, like if I was to split this into 3, because we have, say, 30, 60, 90, 120, 150, 180, and then we also have 210, 240, 270. That means now if we move it over 60, now we have our starting point here at 60. From 45 we're going to move it, or this point here, 60 plus 90 is now going to be 150. So that's should be something like that. And then our point ended at 180. Now it's going to end at 240. And that is that. So we actually have 2 more things to do now. We have let's do this one next, our number 3 here. Let's see if I can get a different one. This one is going to be with the 3, and that's basically a vertical stretch of 3. So exact same graph, except now the peaks or the amplitudes are going to be multiplied by 3. So now we have say 2 and 3. So now this is going to get stretched out. So the peak is now going to be here. So just like that, you can see this orange one got stretched by a factor of 3. Now the next one is even simpler. I may not have enough space on here to do it, but we'll try. This is the full one. I won't even write it again. It's just plus 4. All we're doing is moving this up by 4. So if this is at 3, we need 4, 5, 6, 7. So say 7 there. That's the point. This point from 0 is now going to be here. This point is going to go up to here. This point is at -3, it's going to go here. And then back up to here at 4. And that is our new sine graph. It's a little choppy because I'm not really good freehand. But yeah, I hope that was a little helpful, even a little bit. But yeah, that's the gist of it. When it comes to transforming sine, even cosine graphs, you just start with this one instead of this one, the green one. And yeah, you should be able to do the transformations on your own. Just remember the rules from the parabolas and the quadratic functions, and you should be good. So that's it for this video. I shall see you in the next one. Okay, so in this video we're going to be interpreting sinusoidal functions. So let's get right into it. As our last video, we learned how to graph, or the graphing properties of the function. When we see it, how we can graph it, or how the sinusoidal function transformations, how it transforms based on the function that we are given. So let's just jump into an example. Say we have j of t is equal to 4.1 sine 64.7 t degrees plus 5.8. So, from what we learned in our last video, we see we have a 4.1 vertical stretch and a 64.7 a factor that we're going to do a horizontal compression on. So what we're going to do right here is use this function as a real world problem. So let's define t as time, let's say in years, since May 1992, and let's say j of t is equal to the number of applications for jobs each week. And let's say j of t is represented in hundreds. So if you see j of t equal to 1, that's equal to 100. And this model, j of t, this function is going to basically represent the demand for employment in a particular city. So we have our function, we know what t is, we know what j of t is, we know our sine function is a wavy line. So basically we're going to use the sinusoidal function to represent the demand for employment in a particular city, where t is the number of years since, in this case, May 1992. J of t is the number of job applicants in hundreds for each job, for jobs each week. So I'm going to now graph this very quickly. I know that I should have if I plug in 0 into t, so when t equals 0, let's say that's t, and this is j of t. Let's say that is about 1, 2, 3, 4, 5, 6. Let's go up by 2, 4, 6, 8, 10, 12. And let's say this is 5 these are in terms of years. So, I know that if I want to graph this, my intercept, if I plug in t equals 0, then I should only have, like, all this will become 0, so I'll only have j of t equals to 5.8. So that's basically I'm going to start somewhere there. And then I can just graph this out like I usually would. Well, I have the graph, so I'm not going to make you guys work for it. That'll be in a more complex video in the future. I believe it's 10. Somewhere there it should. And then come down to about here. Let's pretend that this makes sense. So that is 1, 2. I can actually go up to here. That's 3. Let's pretend that each one was the same. I'm just not artistic. So now, once you graph this out, it becomes very easy for us to find the period of this. So I did all the heavy lifting for us. So we're not going to go through it in this video, but in a future video we are going to find the max and min of this of sinusoidal functions, but not in this video. So for now, I know my max is it should be no. I will get on that. I'll put this aside for now. Another thing we are going to find is the period. And you guys remember period is from here to here. So you could take a period or any two peaks. So say you took right here and say somewhere over here, and then we can use the two peaks. So I know that this peak is about 6.9 at t. Sorry, like right here, 6.9. I know this peak right here is 1.34. So our period, we can do it from here to here, or here to here, or bottom to bottom. But peak to peak, we're going to do 6.9 minus 1.34, and that'll give us our 5.56 number. Now, the question in interpreting sinusoidal functions, what it all comes back to, is the question that we want to answer: how long is the employment cycle? And that question, when asked, go for the period, because we know one cycle is like all the way like this, but we know it repeats itself at a certain amount, so we're going to go peak to peak, and that'll give us 5.6. So now let's look at the next piece of information that we're going to do. Let's look at another question. What is the minimum number of is the same each time. So from our graphing, we know that the minimum is about here. I know it's 1.7, but this is in 100, so we're going to say the min is 170 applications. Again, this is all done through graphing. In a future video, we are going to actually break down solve for the min and max here. But for now, I just want to interpret a graph. Given that we know all these values, what information we can take away from the graph and whatnot. But yeah, one final thing we can take away, or question we can answer, is right here. 10 years after May 1992, so say May 2002. How many job applications do we have? So we plug in, well, here we can just go here and find it. The peak is actually not at 10, or sorry, the bottom peak is not actually at 10, it's a little past it. But you could actually plug in 10 into here and solve, just punch this into a calculator, and then what you would get, J of 10 is equal to 1.88, and then say therefore there were 188 therefore there were 188 applications in May 2002. So I know for some of you more advanced folks, this isn't really a challenging video, or I don't know if you learned anything here, but I just wanted to make a video on how we can take or pull data from a wave. Once we understand what everything is representing, then we can just pull data from the wave. So I hope that was helpful, or at least if it helped calm some nerves, or maybe rattled your nerves, you never know. But yeah, that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to try to solve a problem using sinusoidal functions. So let's say we have somebody sitting on a Ferris wheel, and this Ferris wheel, this person, they know that it takes them 10 seconds to get to the very top, and the very top is 11 meters, and it takes them 10 seconds. And then we know that this person is going to come all the way back down, and then at the very bottom they'll hit 55 seconds, they'll get to 1 meter. So the question now is, can we develop an equation of a sinusoidal function that will basically model this person's height above the ground, right? And once we have that model, then we can find out where this person's going to be at 78 seconds if this continues. So let's start by plotting this. So let's do 11, they were at how many? 11 seconds. So let's do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we know at 11 seconds they were at 11 meters. So this is the height in meters, and this is so at 11 seconds they were at 11 meters. So let's say I was there, and then we know they were at 1 meter at 55. So we have a max and a min, so we know it will eventually look like something like this. Right? And basically, we know it's going to take the same amount of time to come back up to the same point. So we know that the difference here is going to be, let's see, if it took from there to there, 55 minus, well, it took, at 10 seconds, it took him to 11, and then back down to 45. So we have 45 seconds from top to bottom. So it should take him 45 more seconds to go back to the top. So if at 55 we add 45, we have 100. So we should get back to 100. And there we go. We have kind of a rough sketch. So, now, let's look at this graph. Okay, so, what's one of the first things we can look at? We can look at our vertical translation. So, when we look at our vertical translation of the axis, remember the sine function starts off like this. So at some point, this line in the middle was moved upwards here. So the way we're going to find out where that line is right now, we just need to find that imaginary line going through this. So we're going to take the max and min. So that'll be, our y value will be 11 plus 1 over 2, which will give me 6. That means right now the line is up at 6, which means this sine function has moved upwards by 6. So we have that information here. Up 6. What else can we look at? We can look at the amplitude. Yes, so our amplitude, let's look at from 6, which is our line here. That is 11 up here. If this is 6 and that's 11, then our amplitude, all even here, 6, and our bottom point, our throw, is 1. We know our amplitude is 5, which means we've had a vertical stretch by a multiple of 5. Amplified. So there are two things right off the bat. I was able or stretch. Let's say our horizontal compression, let's call it K, a value of K. So let's look at so how can we figure out the compression? So I know for a sine wave we have a period of 360 degrees, right? So 360 degrees. So what we're going to do is see what our period is here, and our period is going to be our original 360 degrees compressed or expanded by a value of K. So we have to find out what that is. We know that from peak to peak we have 90 seconds. And how did we get there? We got 90 equals 360 over K. So when we cross multiply or rearrange, we have 360 over 90. So we have K equals 4. So we have a compression of 4. So now I'm just slowly tearing this problem apart, trying to figure out what's going on here. So let's look at a horizontal compression of what could it be? I think one of the easiest things we could do so if we look at, instead of a sine function, let's look at a cos function, because a cos function starts at 1. So we know that it will start here at 1 and go like whatever it does. I know that this, well, I could convert this into a sine function and find this here, and then find out the distance from here to here, and say it had a vertical shift by that much over to that side, or even the other way. But for simplicity, I'm going to use a cos function because it starts at the intercept, so I can just say that this part here, if I moved it over to the right by 10, then I will have a cos transformation. So now I have 1, 2, 3, 4, 5. I have all these pieces of information. Now I can actually put this together and just write out a cos function. So we do have ry equals a cos k x minus d plus c. Just by plugging these in, I know my c value is this. This is my d value right here. This is my k value right here. This is my a value right here. So I can just rewrite this. Y equals 5 cos 4 x minus 10 degrees plus 6 So I just plug in 78 here. And then I'll have 78 minus 10, 68 times 4, 272. So that will be 5 cos 272 plus 6. You plug this in. Cos of 272 is 0.035. 5 times that plus 6 is about 6.17 meters, so somewhere here. On the, well, if the tallest is 11, so you'll be somewhere here, either on that side or that side. So there you have it. Actually, you can even eyeball it here. 6.17 at 78 seconds. So right about there. Yeah, 6 point something. Yeah, looks good. So that has been us using our brains to solve a problem using a sinusoidal wave. That is all for this video, and I shall see you in the next one. Okay, so in this video we're going to be looking at arithmetic sequences. So, by definitions, let's look at a few definitions actually. Let's look at a sequence is ordered list of numbers. A term is a number in a sequence. So now let's define arithmetic sequences. So a sequence, an arithmetic sequence is basically a sequence, an ordered list of numbers, which has the same difference. So you can do 2, 4, 6, 3, 6, 9. So yeah, that might just sound pretty straightforward, but yeah, that's what arithmetic sequence is. Another term we're going to learn today is a recursive sequence. Basically, a recursive sequence by definition is a sequence in which one term or more is given, and each successive term is determined from the previous one. So basically, like if you start with number 1 and then you do whatever the number is times 2 plus 1 plus itself, right? So if you multiply this by itself and then add it to itself, you get 1 times 1 plus 1 is 2. Then do the same thing to this. That would be 2 times 2 is 4 plus 2 is 6. So that sequence, so 6 times 6 is 36 plus itself, 42. So this is a recursive sequence. So we're gonna have a lot of fun in this unit. So we're gonna start right off the bat. Let's start with this. 3, 12, 21, 30. Let's find a formula that will easily find or give us what this is, right? So now that I'm looking at it, it looks pretty straightforward. So let's just eyeball this, say that the difference there is 9. The difference there is also 9. The difference there is also also 9. So, how can we express this in terms of a formula? Any takers? Okay, let's try. So let's call this n equals 1, n equals 2, n equals 3, n equals 4. So we have to find a way to write this out in terms of n. And basically say if you plug in like the 8th number into n, say n is equal to 8, our formula, we should just be able to swap the n for an 8 and calculate that number. So, let's look at this step by step. So, we know that we have a difference of 9 each time. So, let's start with the first one. T of n is equal to, let's say we start at 3, plus n minus 1 times 9. So now if we were to expand this because of our first term, because we do not start at 0 or 1, so nothing easy, our general expression is going to have to start off of 3 and then do some sort of arithmetic. So, because we start at 3 and n is equal to 1, right? 1 minus 1 will give me 0, and I won't do anything here. It'll just be n equal to t at 1 is 3. But when we have 2 minus 1 is going to give me 1. 1 times 9. I'm going to add 9 here 1 time. And if we do 3 minus 2 is equal to 2. Sorry, 3 minus 1 is equal to 2. And 2 times 9 is 18. 18 plus 3 will give me 21. So an easier way is to simplify this. Just expand the brackets and collect like terms. So 3 plus 9 and minus 9. So let's just collect like terms and get 9n minus 6. And that is our formula for this sequence right here. So yeah, that may have looked a little complicated, but the more you do it, the more easier it gets. So let's look at maybe another solution. Maybe I can write it. Maybe I have space here. So, we'll just going back to this. You can plug in these numbers. N equals 1. When n is equal to 1, you have 9 minus 6. You get the 3. Same with the 4. If you put 9 times 4, you get 36. Minus 6 is 30. That way you can like ... go all the way. N equals 100. And just do 100 times 9 is 900. 900 minus 6 is 894. So like that's the reason we use these arithmetic sequences. It helps handling big data. So let's look at another problem. Let's say that the 7th term is 53, and the 11th term is 97. So, how are we going to do this? So, let's look at this logically. So, we know that this arithmetic sequence, so every time when we see arithmetic sequence, we know that it's going to increment by the same amount of every time, right? So, we know that the 7th is going to be 53, and the 11th is 97, right? So now we want to find out we want to find the 100th term. So if our 7th and 11th are these numbers, we know that 11 minus 7, say I'm going to give it a d, a variable, d being its turn in line, or a term, is the same as 97 minus 553. That'll give me 4d is equal to 44. That means over these 4 times, it's gone up 44 times, so d is actually 11. That means every time that this happens, the pattern is that it goes up by 11. So now it's very easy. All I have to do is just increment it by, say, I could start at 97, because I know 97 is at 11. I can say 97 plus from 11 to 100 is 89 more times. And I know that will give me 97 plus 979. That'll give me 1076. The reason why I didn't do 100 times 11 is because I don't know if this sequence actually started at 0. But I know that it went through 11. At 11 it went through 97. So if I just start at 11 and add 89 more times, I'll get to 100. So yeah, that is arithmetic sequence for us. I hope that this was useful in some regard, but yeah. I hope you liked arithmetic sequence, and I shall see you in a future video. Okay, so now we're going to look at geometric sequences. In the previous video, we looked at arithmetic sequences, which increment by a certain amount. Geometric sequences, on the other hand, increment by a certain ratio. So, let's just jump into a example. So, let's say we have a problem where we have the first term is 9. And the common ratio is 2. So, given this information, let's find the 13th term. I want to find the 13th term. So, the way I'm going to find this, well, let's this example, let's just write this out. Let's just plot it out. Let's do, say, we have n and then t of n. So let's say at 1 we have 9. Right? So at 2, when we have a ratio of 2, we're gonna just do 18. At 3, again, double. 36. 4, we're gonna have 72. At 5, we're going to have 144. And at 6, we're going to have 288. At 7, we're going to have 576. At 8, we're going to have 1152. At 9, we're going to have 2, 3, 4. And then at 10, we're going to have 46, 8. At 11, we're going to have 92. 92 is 16. And then at 12, we're going to have 18, 4, 32. And finally, 36, 864. So, that was a lot of doubling. So this is the manual way that we can actually find these things. So, we use a geometric geometric sequence, so that we don't need to write it out like this. I can just take this common information and just plug it in and say, hey, this is the number that I need, and that's what I'm going to get. So, let's look at a formula for this geometric sequence, so that next time we don't have to write all this out. So, if we were to actually write this out, see, our first number is 9. Let's call it A. Our second number is A times our ratio 2, right? But our third number is A times our ratio times our ratio again. So that would be AR squared. The next one, AR cubed dot dot dot. This one you could even say is AR to the power of 0, 1. So, if this is our n term, if I write our n terms here, this is going to be 1, 2, 3, 4. So I could say that this exponent is n minus 1. So r is actually to the power of n minus 1. And boom, there you go. There is a formula for a geometric. This actually defines it defines any geometric sequence really. So I could just plug these numbers in. A equals 9 times 2 to the power n minus 1. There you go. Now I could just plug in n equals 13. Punch that into a calculator. I'm going to get that same number. You don't believe me? Try it. 95%, that's like me multiplying it by 0.95. 3 times 0.95, that's how much it's going to end up. Like I start with 3, and then I multiply by 0.95, and then the year after it's going to be 3 times 0.95 times 0.95, because I'm taking this value here and multiplying it by 0.95 because that has lost 5%. So now we see that our A value is 3, our R value is 0.95. And there you go. Now if this word problem asks me how much of this 3 kilos is going to be left after 100 years, very simple. I just put in, I plug in 100 into there, and then just solve. So that'll be 3 to the power of 0.95, 100 minus 1 to the power of 99. And then punch that into a calculator, I'll get 0.019 kg. That is some very, very slow deterioration. So, let's actually do one more example. In which it looks like we're working backwards. So let's say we have a sequence where we have 52,612,659, comma 17, 5, 3, 7, 5, 5, 3, comma. Oh no. That's one term, that's 17,537,553. Then we have a bunch of terms, and then we end with 11. My question here is, in total, how many how many terms are in this geometric sequence? So, let's start off with our good old formula, A, R, n minus 1. Remember, our ratio could be a number that makes your, like if we have, before in our previous examples we had a 2 or a number that would increment. Actually, our last example was decrementing, what we're left with. It kept shrinking, so yeah, our R value can be smaller than 1, and in which case it will actually make your value go smaller. Our sequence will go to a smaller number. So let's say I have 52,612,659 as my A value. Then I have R, which is my R value. Actually, I can just divide these two, see what the ratio is. And if you do that, you'll notice that it's actually 1/3. So I'm gonna put 1/3 here to the power of n minus 1. So if my last number is 11, I want to know what my n value is that I'm going to get 11, because this formula, if for this formula to give me 11, that means I've gone through all the n terms. So in that case, if I work backwards, then I will actually find out the total amount. The n value, the total number of values in this. So if I was to skip all the math, which would just be, because we haven't actually covered logarithmic math yet, but our n in this case would be 15. The correct way would be to just divide that, and then do think should be a good intro for geometric sequences for this video. I'll stop this one here, but yeah, I hope you enjoyed this one, and I'll see you in the next one. Okay, so in this video we're going to be creating rules to define sequences. So let's just jump into a sequence. Say I have the numbers 1, 8, 16, 26, 39, 56, and 78. Now let's say I want to find the next 3 terms that come into so I want to find out what these 3 are given this sequence. Let's start trying to figure this out. So a very easy way to do this is to just write it out in terms of a chart. So let's do let's look at the difference. So let's look at the difference between these two. The difference there. 8 minus 1 is 7. So now let's look at the difference from here to here. The difference here is 8. And the difference here is 10. So I'm not seeing a pattern right away, but let's look at this one. The difference there is 13. And let's look at the difference there. That is 17, and the difference there is 78 minus 56, that is 22. So right off the bat, I do not see any differences when I'm incrementing here. But what I can do is look at the difference again. Second difference, so from here to here, that is a difference of 1, and the difference from here to here, it's 2, and the difference from here to here is 3, and there, it's 4, and there, it's 5. Now I have a uniform pattern that works for all these sequences. So, starting at 7, I increment the amount that is being incremented by 1. So here, I add 1 to get to there. The next time, I add 2. Next time, I add 3. Next time, I add 4. Next time, I add 5. So if we were to continue this, so at 78, before I jumped, I was at 22, and that was an increment of 5. The next increment has to be by 6, so plus 28. So now 22 plus 6 is 28, and I will add 28 to 78, and I will get 106. Now I know the next one I have to add plus 7 to that, so another 35. So now I'll add 106 to 35, and I'll get 141. And then we're going to do that one more time. So this number has to be incremented by 8. And so 35 plus 8 is 43. And 43 plus 141 is 184. So there are my three numbers that are going to be, or my next three numbers. And I could continue this pattern by adding 9 and whatnot, and just continuing on and on and on. But yeah, that is basically in this example we have looked at all the terms, and then we went in and looked for a pattern, and we found the pattern that the amount that this was being incremented by was being incremented. So that's the rule that we found when solving this. So now we can look at, let's do one more example, just to nail this in. Let's look at, let's say we do a pattern with fractions. This is our sequence we're going to start out with. Okay, so let's look at any rules that we can find here. So let's just by looking at this, we see that individually the numerators do have like a pattern going on. So we know that if we were to label this like n equals 1, 2, 3, n being the term, if this is n equals 1, this is n equals 2, blah blah blah, 3, 4, 5, 6, 7, n equals 7. We can write a rule for this, for the numerator first. So we can say that the numerator starting at 3, n is equal to 3 plus n minus 1 times 2. And this is because I see an increment of 2 uniform along here. So if I was to expand this and just simplify, I would have n equals 2n plus 1. So at n equals 1, I have 1 times 2 plus 1 is 3. And at 15, at n equals 7, I have 2 times 7, which is 14 plus 1. That's that. So this will work for the numerator all across. Only thing that's left now is to come up with a similar rule for the denominators. So if you have a very sharp eye, then you have right away noticed that the denominators 4, 4, 9, 16, 25, 36, 49, and 64. These are all squares. So we could easily just like rewrite them as 2 squared, comma, 3 squared, comma, 4 squared, 6 squared, 5 squared, comma, 6 squared, 7 squared, 8 squared, 2, 3, 4, 5, 6, 7, 8, all squared. So there is our rule that we found right away. So then we can write a rule for this as well. So we can say that the denominator at n, when n equals 1 here, 2, 3, 4, 5, 6, and 7. We can write that this term, whichever one we're looking at, is equal to n plus 1 squared. So you see how n is equal to 2, but it's 3 being squared. Here, n is 7, but 8 is being squared. So we have n plus 1, whatever term it is, squared. And this is our denominator term. And so the rule that we can write for this, let's represent it as d of n. For this sequence, we're just going to put the numerator over the denominator. And there you go. And you can basically say that n is equal to all real numbers. So, I hope that these are very simple examples, but I hope that they kind of like show you what we're talking about when we try to create rules for sequences to define the sequence. So here we can basically define it mathematically, the increments of the sequence, and this will come in use in the future. If you are going into a tech field and want to apply to some big tech companies, they do have these sort of IQ tests they send you to do online, in which they give you a sequence and then they tell you to or they give you 30 seconds to 40, no sorry, they give you 90 seconds to come up with the next term, only the next term, and you have to very quickly come up with the rule or identify the rule. But yeah, I know that company that does it is IBM, but maybe they don't do it anymore, but yeah. Fun fact. So that's it for this video, and I shall see you in the next one. Okay, so in this video we're gonna look at recursive sequences. So we've done a lot of sequences, but now we're going to look at a recursive sequence. So that is, a recursive sequence is something that basically, how should I put it? The next term that comes in a sequence, say you have like terms A, B, C, D. Term B will depend on A, whatever A is. Similarly, term C may depend on what B is, or in some cases what B and A is, or are, and like that as well, and on and on. That is a recursive sequence. So we're going to look at an example of this in a very popular sequence called the Fibonacci sequence. So, given that the first 5 numbers of the Fibonacci sequence is 1, 1, 2, 3, and 5, can you determine the next 5? I want to find out the next 5 terms. And the Fibonacci sequence is mainly one of the most popular examples when it comes to recursion, even in programming. So that's a fun area to explore recursion. So let's look at the Fibonacci sequence. I'm gonna write Fib for short, and I'm gonna write new, the new sequence here. So I'm just gonna write a chart here. So the first 5 are 1, 2, 3, and 5. So let's look at how the Fibonacci sequence actually works. So let's look at the 2 numbers that are around each of them. So this first, given the first view, we can see how these are actually added. So we can say that this number, or I think if I draw it out for you, it would make more sense. So let's draw out this 1 plus 2, which comes from here. And that will give us this term here. And if that didn't make sense, wait till you see this one. 1 plus 3. Oh, sorry. Yeah, I might be confusing myself here. Okay, let's scratch this one, because I think I drew this wrong. Let's start fresh, because I made a boo-boo in the chart. 1, 2, 3, 5. So the way these numbers actually work, the way we get this number here is actually the previous 2 terms. So this term here and here, 1 plus 1, that is this term. It's the previous 2 terms. And then the term, when you look at this term here, this is the sum of the previous 2 terms. So we have 1 and 2. And then when you look at number 5, you have the previous 2 terms, 2. 2 and 3. That's what 5 is. So if we were to continue this, 1, 2, 3, 5, what would our next number be? Our next number would be our previous 2 terms, 5 and 3. And we would add them up and we would get 8. And how about the next term? Our last 2 terms were 5 and 8. So that would give us 13. And then if we were to look at the next one, 8 plus 13, we're looking at 21. And then the next term, 13 plus 21. Let's do some mental math. That is 34. Yeah. Let's do one more. As I said, we want to do 5. So 21 plus 34. That'll give us 55. And we could continue this on forever. But yeah, that is basically what the Fibonacci sequence is. You just keep adding the previous 2 terms. So without knowing the terms prior to them, the 2 terms prior, we cannot calculate the next term. So there actually is a formula for the Fibonacci sequence. I won't go through that here, but if you didn't know the Fibonacci sequence and you had a recursive formula, I couldn't just like give you let me write those other terms down. 8, 13, 21, 34, 55. I don't think I could give you this until you have at it. I couldn't give you that much and say go at it. Because, well, you might be able to based on the information there. 5 plus 8 is 13. So you could assume that these two would give you that. Yeah, I guess it is possible. But the most important part about recursive sequences to understand is that the next value depends on the previous values. Well, the terms depend on one. Terms depend on one or more of the previous terms. That is what a recursive sequence is referring to. So yeah, this was a relatively short video compared to the other ones, but it was just a quick intro to what's it called, recursive sequences. So yeah, join me next time when we get into series instead of sequences. We're gonna learn series next. But for now, that's all for this video. I shall see you in the next one. Okay, so today we're going to be looking at arithmetic series. So we know that, well, we learned what arithmetic sequence was. Now we're going to learn what series are. So we know that, well, by definition, a series is a sum of the terms in a sequence. So given a sequence, we're going to look at the sum. That's what we mean when we talk about a series. So in this case, we're going to be looking at the sum of the terms in an. That's what an arithmetic series is. The sum of the sum of the terms in a arithmetic sequence. So another thing we have to define right off the top is S of n, n being the terms. And S being the sum of these terms, all the first n terms. However, you want to define n to be, it could be ambiguous or it could be defined. So let's start with a very, very vague example. Let's look at this sequence. A plus D. So this is the series that I'm writing. Not the sequence, because the sequence could be 1, 2, 3, 4, 5, 6. And basically this would be A equals 1 and D would be 1 as well. That's the difference. Or I could start at 5 and increment by 2, then A would be 5 and D would be 2. But writing it like this is just saying like, oh, that is the exact definition of the terms that we're writing. A plus 2D plus A plus 3D plus dot 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 dot. That goes on forever. So I want this in a series now, a generic formula. And this will go until the term t of n. That'll be whatever. So that is what we're looking at. So if we were to break this up and write this out, I could very easily, give you the formula, but yeah, I think this might be too complex to derive. So I'll just write out the formula for what is actually known as the causes. The mathematician who came up with it. So if we were to write out the formula for this, it would be S of n is equal to n times 2a plus n minus 1 times d over 2. And it's actually quite interesting how this is derived. Lots of big numbers, big data, but if you were to write out the sum of all this and just try to factor everything out of these, this is how it would look after all the simplifications. Even this, we can actually simplify further for our purpose. A plus A plus n minus 1 times d. And that's just, 2a plus that is just the same as saying a plus that. So now I'm going to factor out this into there. So now I have something very interesting here. I know that A is my t at 1, or n is equal to 1. So remember, t of n being the term, t1 is A. So I can substitute that. But this term right here, on this side, a plus n minus 1 times d, it's actually the last term, or the definition of any given term. So whatever the last term is, so if this is t at 1, or like say, I look at this term right here, 1, 2, 3, 4, 5, 6, I can rewrite the term as a plus n minus 1 times d, because that's what's going on here. A plus the term number, where here it's 1, here it's being multiplied, being added to 1, so n equals 2 here, n equals 3 here, n equals 4 here. So I'm multiplying the arithmetic series is being incremented by a certain amount of times, that is n minus 1 times. It's not being multiplied like this is n equals 4, this is the fourth term, but d is not being added 4 times, added 3 times. So 3 is equal to minus 1, because n is 4 in this case. So if this is true for any t of n, so I'm going to rewrite this term right here as n times t1, which is this one, plus t of n, which is this one, and given term over 2. And that is the sum of all the sequence after all the simplifying and expanding and simplifying. So if that did not put you to sleep, let's look at a real world example. Let's look at, say, a theater. Say we have a theater, right? And in which this is the front of the stage, and then the front row has a certain amount of seats. Say the front row has 23 seats, but then the row behind it has 23 plus 4, and every row behind it you add 4 more. So now, if the first row 23 seats, and every row is 4 seats per row extra, and I have 50 rows. Now my question is, how many seats are in this theater? So now this is a perfect time that we could use the arithmetic series, because we have a consistent increment and we can just plug it in here now. So remember our formula that we derived, this one, we can actually write that in here. So let's write that. So now let's look at how many terms do we have. We have 50. And we also have our initial A value, which is 23, right? And then we also have a D value, a difference, increment, which is 4. And now it's simple plug and play. And honestly, this topic has always been easy. It's just, you have to understand where this comes from. Once you understand that, it is just plug and play. So we can do our 2 times our A value, 23, plus 50 minus 1 times D, which is 4, over 2. Punch that into a calculator and you get 6,050 seats. So there is a real world example on how we use this. I hope I didn't confuse anyone too much with this one, Gauss's method. Maybe in a future video we'll actually go into deriving this. But yeah, for now I'll just leave it as an intro. But this is the formula to, I guess, keep an eye out on. So yeah, that's all for the arithmetic series. I'll see you in the next one in geometric series. Okay, so in the last video we did arithmetic series. In this one we're doing geometric series, which is also the sum of terms in a geometric sequence. So let's jump right into this one because last one was confusing enough. So let's start with actually deriving the formula. Well, we'll see if we can derive it. Let's take a geometric sequence of t of n is equal to a r n minus 1. And remember, this is the geometric sequence formula, or the way to define t of n on any given geometric sequence. So, if you were to write this out, say from the beginning of a sequence, so say R, so let's write the sequence. So this is the formula for the sum of a geometric sequence. I know I proceeded to just write it instead of deriving it, but after looking at it, I think it's way too complex for this level. Well, maybe it's not, but it's just a whole bunch of writing out this sequence in terms of like r of s of n is equal to the first term, ar plus ar squared plus ar cubed dot 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 plus, when you get to the end it's ar n minus 2, n being the number of terms in the what do you call it, in this series or this sequence, plus ar n minus 1 plus ar of n. And then when you have this one, so when you write out the sequence in these two ways, you can actually subtract the two terms and actually end up with this. So if this is equation 1, this is equation 2, and you subtract the two, both of them representing the full written out version of this in different ways, then you will actually get r minus 1 times s of n, and then obviously these will be zeroed out except the last term. Sorry, this one should not have that. So this will come down, these will cancel, everything in the middle will cancel, that's just factoring out the a. So you have ar to the power of n minus a. Then you factor out that a and you get that. So you could actually cross multiply. Multiply both sides by, divide both sides by that goes away. And that's how you end up with this formula right there. I know it's confusing to see, but yeah, it's a very, very tedious process. But yeah, I think if we look at an example, then you actually will be able to understand where this formula is coming from. Let me just write it again. So let's actually look at an example. So let's say we have a sequence in which we have say a fish of some sort is laying eggs, and on the first 4 days you have a certain number of eggs hatched. So day 1 you have 2 eggs, day 2 you have 10, day 3 you have 50, and day 4 you have 250. So given this, find out what would happen, calculate the total number of eggs over 10 days. So because we're looking at a sum here, we're going to look at the series, and because this is obviously times 5 times 5 times 5, we're going to be using r equals 5 in our geometric series equation. So now that you have that, we have our initial value a equals 2. What else do we have? N we know is 10 days. That is our last term. So now let's just plug and play. So 2 times 5 to the power of 10 minus 1 over 5 minus 1. And if I do a little bit of mental math, which I'm kidding, I didn't do, I get 4,882,812 x. And I know it's easy to just multiply this by 5 10 more times and just add those numbers up. But say you want to find 100 days or 1,000 days. Like this series, this geometric series formula will really help you out, especially if you learn how to code this into Excel, this one and the arithmetic series. But yeah, the series and sequence formulas and all that is honestly my greatest enemy, because I actually failed a course in university on series and sequences, and I had to retake it. But yeah, all worked out in the end. But yeah, I have a history with it, but don't let it scare you. binomial expansions. And we're going to look at this in a very particular view using Pascal's triangles. Or triangle, not triangles. So, if you look at Pascal's triangle, basically it's a pattern that we can use to expand a binomial efficiently. So when you look at a triangle, you have the first row in which you have, one thing here, and then the next row splits up into two, and then the next row will split up into three, and then the next row will split up into four, like and then you just have to visualize this. So keep this pattern in mind as we look at this. X plus y to the power of 6. I want to expand this all the way out. So, how can we do this? Let's look at the pattern one by one. And you'll be able to see this very clearly once we expand it. So, x plus y to the power of 1 is 1x plus 1y. X plus y squared. If you expand and simplify, you will actually get 1x squared plus 2xy plus 1y squared. And if you do x plus y cubed, you can expand this and simplify it. You'll actually get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. And now you may actually be able to see the Pascal's triangle if I was to write it out like this. 1, 1, 1. So this 1 and 1 is going to give me a 2. And then a 1 on each side. And then this 1 and 2 is going to give me a 3. And then a 1 and 1 on each side. And then here we're going to get 4. And here we're going to get 3 plus 3 equals 6. Here's going to get a 4 and then 1s on the edges. And that's how the Pascal's triangle goes down. So, if I was to write out x plus y to the power of 4, given that this row right here imitated this one, 1 and 1. The next one did 1, 2, 1. The next one did 1, 3, 3, 1. What do you think the next one's going to be? Well, if you expand and simplify, you we're going to get 1x to the power of 4 plus 4x cubed y plus 6x squared y squared plus 4x y cubed, yep, plus y to the power of 4, 1, 4, 6, 4, 1. That's this one. And there you have it. The Pascal's triangle in full effect. And honestly, if we go to the next row of the Pascal's triangle, let's try drawing it out. 1, 1, 1. So there is the 6th row. So I could basically skip all this work and just write this out the way I could, just, I have the 1x6 plus 6x5 y plus 15x4 y squared plus 20x cubed y cubed plus 15x squared y cubed plus 6 x y to the 5 plus y to the 6. And that is how we can quickly expand binomials without doing all the work. So now that you know what the Pascal's triangle is, let's quickly jump into another one. Let's say we have, just keep this somewhere for reference, right there. Let's do x minus 2 to the power of 5. So, very easily I could apply this Pascal's triangle to our, what do you call it? Our binomial expansion here. So if I want 5, I'm basically looking at this one right here. 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. So let's look at how we can write this with our, in this case, last time we were writing with x's and y's. In this case we don't have a y, we have a negative 2. So we could basically just very quickly write or skip to writing 1x5 plus 5, which is the second term, decrementing in power as the second one is incrementing in power. So once you simplify this, you get x5 minus 10x4 plus 40x cubed minus 80x squared plus 80x minus 32. And that's how easy it is to quickly expand and simplify. Like you could even do 5x plus 2y, a separate example, and just go for the third one, which is 1, 3, 3, 1. And like writing that out is also the same way. Just start with the first term. 1x, sorry, this would be 1 and the bracket 5x cubed. And the next term would be 3 with the first term 5x minus 1 of the degree, and then the 2y with 1 plus 3 5x to the power of 1 and 2y squared plus 1 times 2y cubed. And if you simplify this, well, expand first and then simplify, because then if you expand, you get 125x cubed plus 3 times 25 x squared times 2y plus 3 times 5x times 4y squared plus 8y cubed. And that simplifies to 125x cubed plus 150 x squared y plus 60x y squared plus 8y cubed. Very quick for us to expand. It's tricky but doable. The Pascal's triangle, very tedious work, but you can do it. So that is it for this unit. And I shall see you in our next video. Okay, so in this video we're going to be looking at simple interest, a topic that is actually pretty relevant to the real world. So let's start off with a few definitions. Let's look at principal. Principal is the amount borrowed or invested. And then let's look at simple. Simple interest. And that, by definition, is the interest earned or paid only on that original sum of money that was invested or borrowed. So, let's write that. So yeah, simple on amount. So amount is the total value of an investment or loan, where A is equal to the principal plus the interest. There you go. So this is B, this is A. Sorry. I. So now that you have the definitions, we can actually look at a quick example. Let's say you have someone who invests $3,240 at 2.4 simple interest. So, let's say this is per annum. Like this is shorthand. If you write 5% per A, that means per annum, which is another word for that's just one thing you gotta put there. So let's calculate 3240 after the first year. How much interest? So the interest is going to be 2.4%. So we're going to multiply 0.00. Sorry. The interest is 0.024 times 3240. And that gives us $77.76. And if you're wondering why I use this number to use 2.4%, it's pretty simple. Because 100% is 1.0. That's 100%. That means 99% is 0.99, which means 1% is 0.01, and 2% is 0.02, 2.4 is 0.024. So if you see this, don't be confused. When you multiply something by this, or if you want to multiply something by if you want 75% of something, you can just multiply like the number, like say 10. I want 75% of 10, just multiply by 0.75. And you're left with 7.5. Same with like, hey, if I take 25% away of 10, you can just multiply by 0.75 because you're left with 75%. So yeah, moving on, let's continue that same problem. 3240 at 2.4%. Let's calculate the number, let's calculate amount and total interest after 20 years. And that's very easy to do. You could actually do it the hard way, 0, 0, 3240. This is the year, this is the interest, this is the amount. When 0.76. Next one, 3395.52. You could do it like that. Or you could come up with a formula, which is 77.76 times t plus 3240. And if you plug in 20 for t, then you get 4795.20. So this is the total that you're going to have after 20 years. That's the amount. The interest is actually this, which is 1555.20. Another thing we can calculate here is that's the gist of the interest here. Let's do another one. Another example, maybe something a bit more complex, so we can actually challenge ourselves. Let's look at someone who invests $48.50 at 7.6% per annum. That's simple. Interest. Now, let's say she wants her money to grow to 8,000. How long does she have to wait? That is our problem here. So let's look at our basics. We have our principal, 48.50. We have our interest rate, 7.6%, or actually 0.076. We have our amount that we want to calculate. So usually we have A equals principal plus interest. So let's put this into our formula. Well, in this case, our simple interest is going to be A equals B plus. Our interest in this case is going to be the principal amount times the interest rate times the length. Now we can solve for t. So A is equal 8,000 is equal to 48.50 plus 48.50 times 0.076 times t. And if we were to calculate this, we'll simplify that, bring that one over to that side. That's going to be 31.50 is equal to 0.076 times 48.50. That'll give me 368.6 t. If I divide, I should get t equals 8.546. So since t is in years, so yeah, about 8.5 years. If you want to be exact, you can actually take the 8 away and say that's 8 years and 0.546 and multiply that by 365. You get 119.2 years and 119.2 days. And you know, 0.2 is a fifth of a day. So 24 over, 5. Yeah. I'm not going to calculate that. Just being extra at that point. But yeah, that's what simple interest is. The interest that you incur or get or pay is the same amount, the original amount on the principal. So, I hope you liked that video, or sorry, this topic. The next one we're going to be looking at compound interest, also known as future value. So tune in for that one. But as for this one, that's all for this video. I shall see you in the next one. Okay, so in this one we're going to be looking at compound interest, or as it's also referred to, future value. So, what is compound interest? And unlike simple interest, which is just interest calculated on the principal amount, and that's what is kept the entire time, compound interest is interest that is added to the principal before the new interest is calculated again. So, say you have like a savings account with like $2,000 in it, and it pays like, say, 10%, which is imaginary because you never get that. 10% of 2,000, after the first year you'll get 2,200, and then again the 10% is not 200 again. That would be simple interest, but in this case you get another 220 because you get 10% of this value, the new value. So that would give you another 220. So you get 420. And then again on this, so you get another 242. So you get, 400. 242. I'm jumping ahead. So you get 642. Because it's being calculated on this new value. So this will make your money, instead of going like this, it'll make it go like this. And you want that exponential growth or decay. But in terms of interest, it's exponential growth, or like even in terms of a loan. So another thing we gotta learn is compounding period, and this just refers to the interval at which the interest is calculated. So annually means if you have annually, which is yearly, one time per year, you have semi-annually, which is twice per year. You have quarterly, which is 4 times per year, and then you have monthly, which is 12 times per year. You can also have bi-weekly, which is 26 times per year, or weekly, which is 52 times per year. But this stuff is stuff you already know. So let's actually just jump right into an example. Let's say in this case you have somebody who borrows money. That's usually where compounding comes in. Simple is when you are making the money, when you borrow the money and you have to pay it back. Banks let's say annually. So let's check to see how much he has to pay back this guy if he borrows this money for 10 years. So we're going to be calculating in 10 years in the future. Calculating the future. I wrote it there, but yeah. Which is actually the letter A. In the future. So let's start calculating our 4.6% compounded every year. So if we were to do the math, after 1 year, that's our interest rate R, and this is 1. After 1 year, you would have to owe back 5543.8. And if you do the same calculation again, now with this new principle, now we do the same formula, but now this is our P. So we do 5543.80 1 plus 0.0. You get 5798.81. And if you do it again, now with this as our principal, 5798.81, 1 plus 0.046 times 1, you get 6,065.56. So clearly, the one thing that we're doing again and again to this number is multiplying it by this, which is actually 1.046. So instead of doing this over and over again, I could just multiply this a certain amount of times, right? Which actually is t. So in our case, I could actually just put in my initial 5300 and multiply that by 10 times by this bracket, which is this number, to the power of 10 times. And guess what? That'll give me the exact number I'm looking for. 8309.84. After 10 years on this loan, you would have to pay that much back. How about we look at the same one? Let's see. Actually, let's look at a new one. Let's look at an investment at this one. On this example, let's look at a $5,000 invested. We're going to invest at 4.8% compounded quarterly. So let's say that we have some parents who invest $5,000 into an account that pays 4.8% and is compounded quarterly. So at birth, this is now we want to find out the amount that this will grow to at 21 years old exactly. So, one of the first things we gotta do is, well, I forgot to write this properly. This is actually invested at 4.8% per year, but it is compounded quarterly. So, this 4.8% is actually for the whole year, but the compounding that happens quarterly, we actually have to divide by 4 because that means 4 times a year, so 4.8% over 4 is 1.2% per quarter. So every quarter it's going to compound the interest by 1.2%, and over the year that would be 4.8%, but let's plug this into our formula. But first we need to find the term in terms of how many quarters. How many times we're going to multiply this into our principal for 21 years. 21 years equal to how many quarter years? Well, that's simple. We just multiply that by 4, which should give us 84. So, we have 84 compounds at 1.2%. So let's write this down now that we have interpreted our data. So, we have our principal of 5,000 times 1 plus 0.012 to the power of 84. And if you push this into a calculator, you will actually get $13,618.62. So, there you have it. Compounding interest. The basics, actually. So, take this and run with it, and make sure you get your best bang for buck when you're calculating your future value. So yeah, that is all for this video, and I shall see you in the next one. Okay, so in this video, we're going to piggyback off our last video of compound interest, which we already went over what compound interest is and how compounding periods work and whatnot. But in that video we did future value, in which we calculate how much a current investment or loan will cost or earn in the future after a certain point. In this video we're going to look at present value, which is basically us calculating the principal we would have to invest now to get a certain amount, or to get a certain future value in a certain amount of time. So, in this case, let's work into it. So, 6% interest per year compounded. So, how much money should we invest today? What is our principal? So, now let's actually do our calculation. So we know that our interest formula is that our amount will equal our principal amount times 1 plus the interest rate over the number of periods that we're going to have, compound periods. So we know that, let's see. Oh wait, one thing that I left out of the word problem is that we want to hit our 15,000 target at 6%, but we want all this to grow to 15,000 in 10 years. So how much should our principal be? So we know our amount is 15,000. Our principal, we don't know. We know that our interest rate is 0.06. And we know that we want to do this in 10 compound years. So it was actually that simple all along. Just rearrange and you have and if you punch that into a calculator, there you go. If you invest $83.75 today and you make 6% interest compounded annually, in 10 years you'll have $15,000. That's kind of what people say to do with the stock market. Invest your money into the S&P 500 index, which has a historical value of 6%. Or was it 10? I can't remember. But yeah, 10 years. That's basically the number you're going to be looking at. So, let's look at another one. Another example. We can solve all sorts of these kind of interest problems. Let's say somebody is investing $5,000 today. And they want to grow it to $50,000 in 40 years. The question is, what should our interest rate be to make this a happy-go-lucky dream? So let's write out our formula. And now we can actually start solving this. Let's plug in our initial values. Should have 50,000. That's I to the power of n. can divide both sides by 5,000, and I should get, and this has to be actually not 40, I do have the time. So 10 is equal to 1 plus I to the power of 40. And now I can solve from here. So if we do some simple exponent math, I could just do root 40 to both sides. And get rid of that exponent there. And now I have 1 plus I. So this should give me roughly 1.0593 equals 1 plus I. And if I subtract 1 from both sides, I'm left with I is equal to 0.093. And this is the same as saying 5.93%. And there you have it. In 40 years, $5,000 today at 5.93 compounded yearly will get you 50 grand, which doesn't really seem like much. But yeah, so I guess we could learn one more thing here. The rule of 72, maybe you heard of it, maybe you didn't. Basically, if you don't have a calculator, this is something like banks, investors, even regular people have used to basically approximate calculations involving compound interest. So basically, if you have an interest rate R% per annum, which is compounded, say, yearly, annually, then basically the rule of 72 means that it will take 72 divided by R to double your, basically to double in value. So say you have 8% as your R. If you do 72 divided by 8, it will take 9 years. 9 years for your, what do you call it? Your investment to double. And you can actually check it. If you plug those numbers in, say you put in a simple $1,000 and you put in 8% and you put 9 here. So this number here, after 9 years, your 8% applied to this $1,000 will give you $1,999. That is why the rule of 72 is kind of famous. I think it's going more famous on TikTok these days than anywhere else, but it's a good thing to have. So that is all for this video. I shall see you in the next one where we do annuities. That'll be fun. So yeah, see you in that one. Okay, so in this video we're going to be looking at annuities. Annuities. Specifically, the future values. So, what this means, or the word annuity, basically means it's a series of payments. Keyword, series of, we really looked into series earlier. A series of payments or investments made at regular intervals. Simple annuity is an annuity in which the payments coincide with the compounding period or conversion period. So, in this case, we're going to be looking at simple annuities today. So, what this means is we're going to be looking at, how should I put it, payment plans and whatnot. Like regularly paid or regularly invested, and all of them will have interest compounded regularly on them, and we're going to try to calculate the future values on these payments. So, let's jump right into one. Let's say we have somebody, or say me, say I want to invest $1,000 at the end of every 6-month period. And let's say that the annuity on this investment is going to earn me 4.8% per annum, which is annually, but it is compounded semi-annually for 20 years. Now, I want to find out what the future value here. So, let's calculate the interest rate first, because per year it is 4.8%, but compounding semi-annually, I am looking at, instead of 4.8, I'm looking at 2.4% or 0.024. And another thing we have to fix here now are 20 years period. Because we're compounding twice a year, I'm going to have 40 compound periods. So now if we actually plug this into our series formula, if you remember I think it was our geometric series, R-1. So, the reason why we're looking at this is because when you look at this payment plan every 6 months, so if you start off with 1,000, the next, the first time you start off, let me reword this. You start off with 1,000, then the first compounding interest that happens, you multiply by 1.024. So that is why we're looking at a geometric series here. So instead of like writing all this out, we're going to use the formula we learned. So we're going to plug in our initial, our first value, A, 1000. And then we have in here the bracket. We have our interest rate that's being multiplied again and again, 1.024 to the power of how many intervals? 40 minus 1. 1.024 is our R. So if you punch this into a calculator, you actually get 65,927.08. And there you go. If every 6 months you put in $1,000 into an account that is earning 4.8% interest per year, compounded semi-annually for 20 years, you can actually save up 67,927. Enough to save up for a used Porsche. Well, let's look at one more example. Let's say we have somebody who puts away or $500 every 3 months into an investment, the annuity at 5.2% per annum. Compounded quarterly. How much will her future value be after 25? So, again, let's start calculating the interest rate per quarter. 5.2% is per year. Per quarter, her interest rate is going to be 5.2 divided by 4, 1.3. 0.013. And the term is actually going to be every 3 months. Quarterly. N is how many times we compound, so quarterly is 4 times a year. 25 times 4 is actually 100. So we could write out that whole geometric series again, or we can skip right to the beautiful chase. Where we have $500 and our interest rate at 1.013. Yep, that looks about right. And now we have $101,487.91. That is us compounding. Really makes you want to save. Let's look at one more. Let's say I want to make monthly deposits into an account. I don't know what my investment is. Let's call it X. let's say this annuity, this account gives me 9.6% per annum, compounded monthly. But in the future, I want to have $500,000 at the end of so how much do I need in my investment? So I could write out my geometric series, which is well, first I gotta figure out this 9.6% per year monthly should give me, well, 96 divided by 12 is 8. Yeah. Well, 0.08, 9.6 over 12 will give me 0.8. So my I should be 0.008. So that's my R value, 1.008. I have my sum value as 500K, and I should be able to solve this by putting in, I don't know what my A value is, but I do know what my interest rate is to the power, well, hold on, 30, I forgot to calculate my N, 30 years times 12, that should give me 360. So, if I calculate this correctly, I should be able to get well, I'll punch this over there. I'll just cross multiply. A is equal to leaving my A value to be $240,000.80. There you go. $240.80, not 240,000. Can't believe I said that. Okay, put in $240,000 into an account every month, and you'll have 500K at the end of 30 years. That makes more sense. So yeah, that's all for the video on future values. Tune in next time for present values, annuities. And yeah, that's all for this video. I shall see you in the next one. Okay, so in this video we're going to be looking at annuities, but in terms of present values. So in the last one we did future values, but in this one we're going to be looking at present values, which means what do we need now, or how much we need to invest now, or yeah, mainly invest. So let's look at say something that is 8.3% per annum compounded is, how much do I need to invest today to provide $500 per year for the next 10 years? That is the question at hand. So, let's start looking at how we could provide this so we don't have to do any extra calculations here, compounded annually. So my interest rate is per year. I got I equals 0.083 and equals 10. So you can just pull up the A is equal to, just say PV, present value, times 1 plus I to the power of n. So present value is equal to A over 1 plus I to the power of n. So let's look at this. Say, if you look at the end of the first year, say PV is equal to $500 over 1.083 to the power of 1. That is PV1 end of first year. And then PV2 is 500 over 1.083 to the power of 2. And if you continue that pattern, PV10 will be 500 over 1.083 to the power of 10. The reason why it's still 500 is because I want 500 per year. That's our target. So, if you look at the way I went about this, then you can see that I'm basically gearing up to add all these together, which again gives me my geometric series. So, let's just skip right into the good stuff and just use our geometric series. I was going to kind of like sneak my way into the geometric series, but I guess you saw right through that. So, I got, well, what do I got? In terms of my interest rate here that I'm using in my series, my series isn't really growing. So, unlike before, where I had the interest rate being multiplied by my amount or my present value, my interest rate is actually being divided by my interest rate. So that'll give me, so if I was to write PV1 out, it would actually be 500 times 1.083 negative 1. And then the next term would be 500 1.08 negative 2 negative 3 and so forth. that's my A value, which is 500 times 1.08 3 to the negative 1. And then I have my R, my interest rate, which is this. To the power of n, which is 10 years, minus 1. All that divided by 1.083 negative 1 minus 1. A little bit more complicated than I like it to be, but let's punch that into a calculator and you get 3310.11. So I would need to invest a sum of $3,300 and, well, 3310.11. I would need to invest that now to provide a payment of $500 every year for the next 10 years. Well, that's interesting. Let's try looking at another example. Something a little bit more lavish. Let's see. Let's look at the exact opposite of an investment. Let's say a loan. Let's look at a loan from a bank. Let's say the loan was for $200,000. $200,000 loan. And let's say the bank charges 6.6% per annum. Compounded monthly. And let's say we're gonna take 20 years to pay this loan off. So let's say I want to take this information and find out how much I'll be paying monthly. So let's start off with the interest rate compounding monthly. So 6.6 over 12 should give me 0.0055. And my end value, 20 times 12, that should give me 240. So my present value is 200 grand. And if you remember our annuity on our negative, on our present value annuity geometric series, let's just write that out first, then I'll start plugging them in. So now that I have all this information calculated, I have my N and my I. I'm going to start substituting. Oh, I don't think I this formula, there's a long derivation for it, but this is the formula for present value of an annuity. So let's start plugging in. Well, like R is the letter R represents the monthly payments I'm going to have to do, and is the number of payments. The number of payments. I being the interest rate, and V being the present value of the loan. In our case here. So if you were to write this out, we have R, which we're trying to find out. And then in here we have 1 minus 1 plus 0.0055 to the power of negative 240 over 0.0055, and this will all equal, we have 200k equals R times 133.072, and when you divide both sides by 133, you actually get R is equal to 1502.94. That will be the monthly payment to pay this off. And that is a hefty loan because the monthly compounding, that's what's really screwing this person up. This person being me in this completely imaginary case, but yeah, that is all for this video on present values and annuities. I might actually do a video on deriving these formulas for present value and future value annuities, and even compounding interest.